Thank you. So today we have the pleasure of having Dr. Ines Bigaran here. Ines is a research associate at both Northwestern University and Fermilab, working in particle theory. She completed her PhD in 2022 in Australia on the interplay between neutrino and flavor physics. Presently, Ines works on standard model and beyond the standard model physics, building mathematical models and tying these together with our present understanding of the world around us, with the aim to complement experimental programs in high energy physics all over the world. And so today, Ines will be telling us all about the standard model of particle physics. So Ines, whenever you're ready, please take it away.
Excellent. All right, can you hear me properly? If it gets weird, tell me. Excellent. So today, I'm going to tell you about a model, and we as particle physicists are kind of, we're both blessed and cursed by the fact that we don't always appreciate how amazing this model is. So this is what we call the standard model of particle physics. And my aim here is to tell you about how we came up with this model and all the bunches of different work that's gone into developing this and what we have now and what we now look forward to in the future. So my focus won't be as much on what we do now with the standard model beyond, from explaining beyond the standard model, but it will be what is the standard model and how does that fit into what we do as particle physicists. Excellent. All right. So this is a standard model, and it's an amazingly effective theory of nature. In fact, you could write it down on a coffee mug like this, or you could write it down as this kind of periodic table of fundamental particles. Now, I know you see this and you go, all right, pretty pictures, but I don't understand what's inside it. So what's inside it? We have these particles along here, and these particles are quarks and our leptons, which I will discuss in more detail later, are the particles that make up matter. So everything that we see around us is made up of these particles. These particles here are the force carriers. So what that means is they're responsible for the different particle forces that we see around us. So electromagnetism and the strong force that holds things together in nuclei, and also things that are responsible, say, for radioactivity. These sort of forces are all carried by these particles here. Now, I'm going to very naively say that this is our final particle and it's responsible for mass. There's a little bit more to that, but I'll get to that later. But this is our final particle, the Higgs particle, that's responsible for how these fundamental particles get their masses. So I want to explain to you now how we got here, because I think that many particle physicists would agree that if I was going to sit down and write a model, they wouldn't necessarily draw this picture. If they were going to go from scratch and just sit down and say, what's the world made up of around us, they wouldn't sit down and draw this kind of mix of things all together. There's steps that we went by in order to get to this point. And the way that we're going to start thinking about this is through the scientific method. So the scientific method, as scientists, we all want to follow the scientific method. We look at something, we see something around us, we observe it. We then question, how does that happen? What is that? We then think about a hypothesis of how perhaps that might be explained. We go on to do experiments, and then we make a conclusion. And after that, we look at it and we think, how good is our hypothesis, and could maybe we come up with a better one? And we repeat in various different ways with various different levels of complexity. So in general, developing the standard model came from a number of series of questions. People asked questions about what was going on around us, and they really wanted to understand the fundamental nature of the universe around us. And that's still what drives us in the particle physics community. So let's dive further into what this process looked like. So you can think of the standard model as what I would say an effective theory of nature. But many people, if you go around the street and you ask them, have you used the standard model today? They would say no, right? Because there are many effective theories of nature. You can think, you can sit, and you can drop something from a particular height, and you know that gravity, as you learn about it at school, is completely sufficient to explain how fast this is going to go until it hits the floor. That's fine. But many people have heard of this idea of gravity being this big mathematical general theory of relativity that Einstein came up with, right? it's perfectly consistent with dropping something from a particular height. But what we're doing here locally on Earth is what's called an effective theory of gravity. And so you can think of this kind of like this sort of diagram, right? A cat or a cow, right? Imagine that you're in a outdoors paddock and you have two cows coming up against each other and they're running into each other and they smash together. You did not need to know the particle constituent of the cow to calculate that that's going to hurt both cows, right? So you know what's happening at the level of cow, but you don't know what's happening at the particle level, and that's totally fine. If you want to go and try and understand what's happening inside the body, how is the body or the body of the cow actually reacting to, say, an infection or something like that, you need to think about things at a cell level. And biologists are totally fine with thinking at things at a cell level for all intents and purposes. Of course, there's some that dive in deeper. But it's fine to think of the body as a cell. And chemists will tell you that the fundamental particle they want to think about is an atom. Because for them, the interchange of electrons and the different behavior of electrons is the focus of their area of study. And at the energies and at the regimes that they're actually dealing with, it's totally fine to just think of the atom. If you go a little bit deeper, the atom itself is made up of particles, and that's the proton, the neutron, and the electron. And people who want to think about, say, nuclear physics and what happens to a really big nucleus, a really big particle that's radioactive, might be totally fine with thinking about things just as protons, neutrons, and electrons. However, if we go even deeper and we want to understand what makes that up, how do we understand all of the things that we're seeing around us, we want to go even deeper, we arrive at something called the standard model. So all of these things are fine on their own at particular energies. So when we look at the world around us, as long as you're only looking for a particular distance, it's fine to think of things at particular levels of complexity. But as a particle physicist, what we looked at is what is the most fundamental point to which we can reach. How is the closest distance we can zoom into the stuff around us and see something that really is the fundamental building blocks of nature. Excellent. So what is matter? So I told you earlier that there was that whole section of the standard model that's responsible for matter. I will assume that you know that matter is the stuff around us. I know when I say matter, it sounds as though there's a D in it. There is T's in it. I just have a silly accent. All right? So matter is made up of atoms. And originally when the atom was proposed, the atom itself, as like an etymology, where the word comes from, means indivisible. So at the time, they thought they'd reached the most fundamental unit of things around us. And what happened was during the development of this, they realized that it wasn't indivisible. And I'm not going to go into the details of atomic theory, but many, many people contributed to this understanding. And ultimately, they reached the point where they understood that the atom was not fundamental. Inside the atom, there were the proton, the neutron, and the electron. The protons and the neutrons are smushed together in something called the nucleus at the center, and then the electrons are around in some particular model. Excellent. So there's heaps and heaps of development that went into understanding the atomic model. And essentially, chemistry is then the study of what happens around those nuclei. What happens to the electrons when it meets another particle, another atom, and then it exchanges electrons, it bonds together with other atoms, and then you've got materials around you. So chemistry is essentially the study of electrons, and it's an exceedingly successful model. And you were able to class things in something called the periodic table, which was proposed at the later part of the 1800s. So at that point, chemistry was sitting down and trying to class their particles depending on their masses and on all of their different properties with reactions that were happening with those electrons. So what we would think when we see this chemistry particle, this particular periodic table, is we still have questions about matter around us that we don't understand. We don't understand, for example, how a nucleus can be stable and how we understand why a nucleus for a radioactive element isn't stable, but the nucleus for another element totally is. I'll get to this a little bit later, but you can think about it like protons are positively charged things, and they're smushed together into this nucleus and they don't repel each other. And trying to understand what that is something that drove us towards development of particle theory. And other questions, for example, is if the atom made up of these protons and neutrons, if these protons and neutrons are actually the most fundamental particle there is, and why then? Why is it that we just have this tiny little negative thing? We have like a slightly larger positive thing and about the same mass neutral thing, and that's just what life is. So trying to understand that and following the scientific method is how we kept going. Now, the first point that I'm going to get to actually comes down to trying to understand the weak interaction. Now, at the time, we didn't call it the weak interaction. We just looked at radioactive isotopes. So what that means, right, we've got a nucleus that's unstable. We see a nucleus, we sit it there, we've got a material really, and we sit it there, and after some time it's decaying, it's spitting out all of these particles around us. And we wanted to understand what is happening in that interaction. So in 1930, Wolfgang Pauli studied the decay of certain radioactive particles, and what he did was essentially invoke something called the conservation of energy. What goes in must come out. The amount of energy at the initial state has to be the same as at the final state. This is the level of mathematics I will be doing here. I can discuss this further in multiple different ways, and there will be points where you guys can ask me questions. So if you have them, write them down, and we'll get to a question slide soon. So just so you know. Excellent. So what essentially was happening is we started with this radioactive particle, and it decays into a lighter particle and spits out an electron. Those particles here are kind of part of a big block. That block essentially isn't moving, but there are a bunch of electrons coming out of it. So what we can do is we can detect those electrons, and we can work out what their mass is. Why isn't the pointer working? Because I didn't turn the pointer on. No? Sorry. It doesn't like me. Excellent. So essentially what happened was that they went and they measured the energies of these electrons. So an electron energy can be measured by the amount of current that it puts through a wire. So what happens is that you have a detector and it detects the electrons by putting a bunch of current through wires. And they measured, instead of just the difference between the energy of this particle and this particle, they measured a spectrum, which meant for some of these electron energies, the conservation of energy didn't work. There was something there that we couldn't see, that wasn't being detected by the detector. And what that was proposed to be a tiny little neutral particle. Neutral because it didn't interact, and it was tiny because it's only taking a bit of the energy away, right? And what happened was that Pauli sat down and he predicted there must be this small neutrally charged particle there that took away some energy. And he was appalled, really. He said in a letter, "Dear radioactive ladies and gentlemen," to the particle physics or nuclear physics community at the time, basically, I'm appalled. I'm proposing something that you can't see. I'm telling you there's a particle there that you can't detect. And so that then Enrico Fermi in 1932 called that the tiny little neutral thing in Italian. So it was a neutrino. And essentially what happened there was that we went from understanding decays to proposing a new particle to try and understand what was going on with the conservation of energy in that decay. So it took multiple years after that, 26 years, to actually discover the neutrino, to detect a neutrino. So there was this particle there, we didn't understand it, we didn't see it, and there was a proposal for the existence of this particle, and then ultimately people went and spent a lot of work on trying to detect it. And this is a very similar story to how you'll find in a lot of the development of particle physics and of the Standard Model. So this also led to the development of what we have is the Fermi-weak interaction. So there was this nuclear interaction was thought of as a weak interaction. It's not the interaction that glues stuff together, but essentially if you get big enough with the nucleus, it's going to decay. So that process was Fermi's weak interaction and led to the production of, or the proposal of these particles called neutrinos. So I've told you that at this point we understand that protons and neutrons are stuck together in a nucleus. There's electrons around it in some sort of way. But I mentioned earlier that if I have a look at the nucleus itself, it's two positively charged particles and a bunch of neutral particles. So these are our neutrons here. That's why it's not working. I'm putting my finger over this point. I got a PhD. So these are our two positively charged particles, and these are our four neutral particles in a helium nucleus. It's hard to understand why these two particles that are positively charged don't repel each other. In fact, you imagine these are like very similar to an analogy with magnets, right? We took two magnets with the same pole next to each other and they're going to spit around and repel each other. So opposites attract, like charges repel. That seems to not be applying here in the nucleus. So the question then is, what's holding this stuff together? And in 1934, Yukawa proposed that without a force holding these things together, the nucleus, no matter how large it would be, would just explode. So he proposed the existence of a particle that would, the existence of a force that would essentially, you imagine if I put two magnets together with enough duct tape, they're not going to repel each other. They've been stuck together by essentially a stronger force. So we imagine that there is another force that's actually holding these particles together in the nucleus, and that was proposed as a strong nuclear force. And it's carried, so essentially we need something, we need the duct tape, right? What's the duct tape that's holding it together? It's some sort of particle that's lighter than a proton, but heavier than an electron, and it sticks the stuff together. So he called these particles a meson. Meson, where mes just means middle. So it's in the middle of an electron and a proton as a particle that sticks things together. So the search then began for what these particles are. We understand there's atoms, we understand that there's a nucleus. Well, if there's a particle that holds stuff together, we should go and look for it, right? So this is the story so far. We have an atom, we have things stuck together, and there is a proposal for trying to understand the sticking together of the nucleus using a strong nuclear force. So at this point, does anyone have any questions? Awesome. All right. So I'm going to give you an aside on mathematics for a second, but I'm not going to call it mathematics. This is Emmy Noether, and she is one of the best mathematicians in history. Einstein said that she was insanely amazing, right? So what she did was, within mathematics, proposed that as long as you've got a conserved quantity in nature, you have an underlying symmetry. What does that mean, right? So, for example, if I do an experiment just here, right? I throw something here, or I do it over there, the results of the experiment are going to be the same. That's something called translational invariance. That tells us that if we do a particular experiment in one axis, and when we move the axis, then the experimental results are identical. That symmetry leads to a conservation law, mathematically, called the conservation of momentum, which is something you may be familiar with. Electromagnetic symmetry, so you can write down other symmetries mathematically, and that symmetry gives rise to the conservation of electric charge. You know, when you sit down and you have a look at a electrical circuit, right? You know the amount of electrons or the amount of current that goes into a particular point in the circuit has to come out of that part of the circuit, And that conservation law is due to an electromagnetic symmetry. What's a symmetry? Well, a symmetry is essentially an invariance. So as I said before, I do an experiment here, I do it over there, it's exactly the same. It's not varying, that's an invariance. But for me, and I think the big takeaway from this slide I want to let you know is that invariance means stability. Stability means that the world, right, follows a particular path due to that symmetry. It's natural for the universe to exert as little energy as humanly possible to do something. It's natural for all of you, although you forced yourself against it, to stay in bed this morning. And you chose to come out here and do physics, which is really cool, right? But the universe, like you in the morning in bed, does not want to do something that acts against what its natural state is. The definition of what I would say is a natural state is something that reflects a symmetry. So, excellent. What does a symmetry do? It explains how nature reacts to a particular change. If I want to understand how a material absorbs different electrons, I follow a rule of conservation of charge, right? So the point of that was to tell you that symmetry is a really important thing that we talk about. I'm not going to go into heaps of detail about it, except to just tell you in a little bit where symmetry was guiding us through developing the standard model. Excellent. So we left off just before saying that we had this particle proposal for how things stuck together in a nucleus. There was some sort of meson particle that stuck the protons and the neutrons together in the nucleus. And what we then wanted to do is go and try and look for these particles. How do we look for a particle? Well, at the time, we didn't have these big particle colliders that you will hear about quite a lot soon in the next talk. What was done at that particular time is looking at something called a cosmic ray. So what is a cosmic ray? Well, we as the Earth exist within the universe, where the solar system around us has a bunch of stuff going on. Things are smashing into each other. There's like light from the sun coming out of the sun and hitting other particles, and then you get a whole bunch of different stuff. All of those particles have to come through the atmosphere. The moment they smash into the atmosphere, you produce a lot of other particles. All these particles are like in low enough concentrations that you shouldn't have to worry about them, but they are there, right? So there's particles around us, and what we can do is we can sit and we can detect them. When a charged particle goes through certain materials, it deposits energy. How is that observed? Well, for example, there is a proposal or the existence, there is this sort of experiment called a bubble chamber. And what a bubble chamber is essentially a liquid that when a charged particle spits through it, it leaves a track. And we can measure and we can detect particles by looking for tracks in that liquid. And if we just sit a bubble chamber outside, we're going to get a number of different particles coming from the universe, these cosmic rays coming through and being detected in these tracks. Excellent. So what happens is then we can look at the track and we see that this particle comes in and it travels in a circle. We know roughly that all these particles come in with the same amount of velocity. And they travel in a circle. So they travel with a particular radius. And we know information about what the force on a particle coming through a magnetic field is. So we put this cloud chamber in a magnetic field. We then look at the different tracks that are made by these particles in the material. And we're able to infer from that information about their mass. So you could follow through if you're interested, but the big point is that this formula here says that we've got a number of known things that we know about our experimental setup. And what we're going to do is we're trying to infer information by measuring the radius. So by measuring the radius of the track, we can get information about the mass and the charge of the particle that's coming in. You don't need to know any more details about the mass. You can do it if you'd like. Excellent. So we want to measure mass and charge of particles that are coming from outer space. So people had done this before. People had sat down and they'd looked at electrons coming from outer space, and they're able to measure the radius of the electron. They see protons coming from outer space, or they smash protons they get protons out of a particular target, and they put them into a cloud chamber, and they measure information about a proton. But in these early experiments, you recall that Yukawa predicted the existence of these particles between the mass of a proton and of an electron. And what was observed in 1936 was that there were particles that didn't really curve as sharply as an electron, but they did come in a particular radius that's less sharp than a proton. Excellent. So there was the excitement that perhaps they had found this meson particle. They'd found this particle that was kind of between the mass of the proton and the electron, and maybe that particle was the particle that's responsible for binding nuclei together. However, when they went and put this particle and smashed it at nuclei, it didn't do anything. So it wasn't interacting with the nucleus like we thought it was. So it's not really the particle that's responsible for holding all these particles together. And this really represents kind of the start of what I would say is modern day particle physics. We've moved beyond just particles that are making up the matter around us. We've looked at this really kind of extraterrestrial particle, and we've found it's actually not really responsible for anything around us. So this led Isidore Rabi, a very famous physicist, to say essentially who ordered this particle? Why do we have this particle? Because essentially what it looked like was just a heavier version of the electron. And why do we need a heavier version of the electron if we've already got an electron? So this was the discovery, actually, not of the particle that stuck things together in a nucleus, but a particle we didn't really see the purpose of. This heavier electron is called the muon. So we still didn't understand at that point what was sticking everything together. But now we've got these extra particles, and this is weird, right? So people started to keep studying the different particles that were produced in cosmic rays. They had a look at the different radii that were coming out, and they found a whole heap of different particles, things that we had no idea existed or why they might exist. And this at the time was called the particle zoo. And Fermi, the namesake of this lab, said that if he could remember the names of these particles, he would have been a botanist. Because at that time, it just seemed like they were just looking for particles and just classifying them and saying, all right, cool, this one has a mass of 2, and that one has a mass of 4, and we don't understand why they exist, but they're not responsible for the matter we see in our bodies. They're just there, and they come from outer space. It's almost like they were looking at aliens, right? So cosmic rays gave us more particles to think about at that point. We're no longer just looking at the composition of matter around us. We're no longer just looking at what makes up an atom. We've now got these other particles there, and we don't understand why they're there. So we know now that what they were actually observing was something called a composite state. There were a bunch of different particles there that were actually potentially made up of even tinier particles. The existence of all these different particles there made us say, all right, wow, maybe there is a reason they're there. Maybe there is a more fundamental understanding of what's going on than just protons and neutrons. So this brings us to a point called the Kwok model of matter. So I said to you before, composite states, and I'm sure some of you went, Ines, don't say weird words at me. So the difference between an elementary and a composite state is essentially what we bring back to is when we first introduced the atom. The atom was this indivisible particle at the time, but we found that there were more fundamental particles below that. What we seek in particle physics is the actually indivisible unit, and that's called an elementary particle. So this is a fundamental particle in nature that can't be broken down into even smaller parts. This is a unit of matter. A composite particle is what happens when we stick multiple particles together. Essentially what was happening in about 1950 was we had all these particles around it and we didn't understand how to organize the zoo. Did we want to sit down and write down something like a periodic table for particle physics? Well, it seems that all these particles existed around us and we didn't know how to put it in a table because all their properties were kind of confusing. Without an underlying understanding of what's going on, you could essentially just put them in different exhibits and tell everyone to go and look at each of the individual ones and not understand anything about how they came together. So what happened in 1961 was the proposal of something called the Eightfold Way. Now, the Eightfold Way is named after the Buddhist principles, but what it really is the proposal of a symmetry and a symmetry model for trying to understand what happens when you have a whole bunch of particles around you, what they could be made up of as a more fundamental particle. So what this led to was the model of quarks. So the idea that a proton and a neutron aren't just fundamental particles, but they're a collection of fundamental particles. And these particles were called quarks. So a proton is a combination of up, up, and down quarks. The neutron are down, down, and up quarks. And there were also a bunch of other particles that they'd seen, like the pion, which is a combination of up and down, kaon, up and strange. And these are a bunch of particles that we were seeing in nature. But what happened at that point is we actually just had these three fundamental particles, and that could make up everything that we were seeing. And that was exciting. So this uses a particular symmetry to essentially think about all possible combinations of these three particles. Excellent. So symmetry tells us what combinations of particles are stable. What particle combinations do we see around us that would explain these different particles we're seeing in cosmic rays, as well as the ones that make up matter? So there are two types of composite particles in this sort of model, and that's groups of 3 quarks, which are baryons, and groups of 2 quarks, which are mesons. So these particles stick together using some sort of hypothetical Yukawa force. But in this model, they stick together because of the symmetries of understanding the theory here. So then the different particle masses. So I said to you earlier, we have these like electron, it's super, super tiny. And then we have the proton and the neutron that are almost the same mass. But we don't really understand why they are as big as they are, or as big as, or bigger than an electron. Well, now we have these protons and these neutrons are actually made up of tinier things. So we've tied together the mass of these particles to the mass of their underlying particles there. So the proton and the neutron are particularly massive, and that mass is tied to the mass of the up and the down quarks. Excellent. So what you may ask at this point is that I'm telling you that there exists a symmetry. When I tell you there exists a symmetry, I mean, Noida would say to me, well, that means there's the conservation law. The moment there's a conservation law, I start to think about forces. So this mathematical understanding of how particles come together was actually hinting at the existence of further forces that we should properly understand. So quarks themselves proposed in this model in, where was it? 1961, were then discovered in 1968. Things were happening fast. So they proposed the existence of these quarks, and then ultimately they were able to discover that this quark model was good. Quarks were now what we thought of as the fundamental particles in nature, the matter. So the story now at this point is that we have up, down, and strange quarks. These are their names: up, down, strange. The strange because it was weird that there were all these particles, right? And we couldn't just, I remember I told you the proton and the neutron are just up and down. The moment we start looking at new stuff, strange stuff, we need to introduce the strange, right? We also know that there exists an electron because that's what we knew about in the 1900s. A neutrino was what we found in nuclear decays. And the muon was this heavier version that we didn't really understand what the purpose was. So at this point, we have particles And we also have forces. So parallel to this particle discoveries was proposals of forces. We understand electromagnetism is something that happens around us all the time. We also discussed earlier the existence of this strong nuclear force, this Yukawa force that was sticking the particles together in a nucleus. We also had the weak interaction, which was what was happening when we had a radioactive decay. And Newton told us that gravity also exists around us, so things fall. Do you have any questions at this point?
Sorry, you said groups of two quarks were called mesons. Is that the same as the proposed particle from earlier that holds the atom together?
So it turns out it is. They were, at the time, not thought to be identical. The point was that the meson being just particle that is in the middle. At the time, it wasn't understood, but it does end up being true that the particle that holds things together is a meson. But we'll discuss that a little bit further in a bit. So I left that there as kind of a, let's see if anyone points out. So good job.
So you mentioned that up quarks and down quarks make up electrons or protons and neutrons.
Yeah.
Does an up quark like have a positive charge? And
Yep. So an up quark has a positive 2/3 charge, and a down quark has a negative 1/3 charge. Remember, we've got 3 particles making up this positively charged thing. So because we discovered protons first, we called that 1. Right? Otherwise, if we discovered other things first, we would have called those 1, and then it would have a charge of 3, right? It's just because these happen to come together in that way, they would give it a charge of 2/3 versus 1/3.
Any other questions?
By this point, have we found out what makes up electrons too, or is it only neutrons and protons?
Excellent question. At this point, electrons are fundamental particles. And I would tell you that now, a lot of people agree that they are kind of fundamental. There are models that exist that make electrons partially composite, but that's something we can discuss in later parts, like after this talk. But the proposal at this stage, electrons are fundamental particles. Yeah. Awesome. All right, so I told you we had all these pictures about what forces are, and we have all these pictures about particles, and we're starting to think when we're putting quarks together that perhaps that's an indication of symmetries of forces. So maybe there's more of a connection between particles and forces than we thought before. So in the 1940s, Feynman, Schwinger, and Tominaga proposed that the electromagnetic force was actually due to the exchange of photons. Photons being these particles of light, but more fundamentally, they're the exchange particle for the electromagnetic force. So whenever we have an electromagnetic interaction, we can think of that as the exchange of a photon. And it also led to the proposal of something that I'm going to attempt to avoid like the plague in this talk, which is quantum field theory. So quantum field theory is an entirely different beast that I'm going to ignore for the purpose of this talk. You can ask me about it later. But all of this can be formulated under this model of mathematics called quantum field theory. But what this essentially means, is, where are we? Excellent. That the photon was being exchanged kind of like a force field, right? Force fields, quantum field, excitations in fields are particles. That's all I'll say about it. In the 1960s, these guys looked at what was done by Feynman, Schwinger, and Tominaga for the electromagnetic force, and they said, well, why can't we do this for the weak force as well? So that force that was responsible for electromagnetic decays. And what they actually did was they unified the electromagnetic force and the weak force. They actually explained it as 2 parts of the same unified force called electroweak theory. What this did was it proposed the existence of 2 additional particles, or 3 if you count both the charges, and the photon. And these particles, when put all together, were what explained the electroweak force. So what they did was they said, all right, we have this particle theory of nature, where the way of understanding how different things are made up are particles, and particles mediate forces in some instances. And they proposed additional particles that would try and understand fundamental nature of both electromagnetism and the weak force. And they were able to successfully do that and propose the existence of these additional particles. And what happens in, say, a weak force, when in a radioactive decay, is that that radioactive decay can be explained by the exchange of one of these particles. Now, I've said nothing about the strong force because at that point, they couldn't say anything about the strong force. We knew Yukawa had previously said that there were these particles holding together protons and neutrons. But at this point, I've told you that protons and neutrons aren't our fundamental particles in the nucleus. The fundamental particles in the nucleus are the things that make up the protons and neutrons, right? So they're broken into protons and neutrons, and then we've got quarks as well. How do quarks stick together? So in my answer to the question before, I said, those are also charged particles, and they somehow are sticking together. So we have an even deeper problem. How do quarks stick together? And this led to the formulation of the strong force. So not the strong nuclear force that we were discussing before, but the strong force. And the strong force is what is responsible for sticking the quarks together into either a meson or a baryon, into these composite particles. And the particle that sticks that together is called a gluon, naturally. So these gluons glue together the different quarks inside a nucleus. And it turns out that that proposal from Yukawa, this meson that was somehow responsible for sticking together the proton and the neutron, is actually a remnant of this strong force that exists at the point where you're sticking together protons and neutrons. The reason for that is complicated, but essentially what I wanted to tell you is that what Yukawa was onto was essentially what we were talking about before when you go from a cell down to an atom. At that point, he was looking at it at the cell level, right? And at that level, it was perfectly fine to explain it by a meson exchange. But the moment you looked closer, you actually found that the real fundamental force was this strong force. So in 1973, these gentlemen proposed the existence of what we call quantum chromodynamics. Chromodynamics is the explanation of what the strong force is in terms of quantum field theory. What I think is cool about this is it's called chromodynamics, and those of you with some European background in languages would know that chroma means color. And what each of these gluons have, and the charge that's conserved in the same way that we think about charge conservation, is actually color charge. So we give them some interesting names in particle physics, but the study of color as a quantity that's exchanged by gluons is quantum chromodynamics. So at this point, if we want to just take a step back, this is the model we have in front of us. We have these three quarks. We have these three leptons. So leptons are the particles that are not quarks. We'll stick it at that. The neutrino, the electron, its heavier guy. And we have these four different fundamental force-carrying particles. So at this point, we hit what's called a golden age for particle physics. People no longer were just looking at cosmic rays. They started smashing particles together. They tried to understand things more than just at the point of just looking for a problem to solve. They had a solution to the problem in a lot of ways. And now they were looking for the particles that those different solutions predicted. So we had the proposal of the W and the Z particles, but we hadn't observed them. So there were a number of different developments in this. So at this point, we understood and we observed the up, down, and the strange quark. We also observed another particle here, the charm quark, in 74. So there were even more quarks than we thought there were. The tau particle, the heavier version even more than the electron and the muon, was observed in 76. Those W and Z bosons that were proposed in the 60s were observed then in 83. And then we went even further and we observed the top quark in 95. So there were now even more quarks at the top, and we actually found out that there were these 6 different particles that made up the quark sector of the standard model. This is a very exciting time because what had essentially happened was that there was a proposal for understanding what was happening with the forces and the different particles in nature. And that proposed model predicted the existence of particles that we had not yet observed. So experimentalists designed experiments to observe them. And those observations ended up being consistent with the models that were written down mathematically, driven by the symmetries we're observing in the world. So ultimately, this came to be called the standard model of particle physics, because at this point, it had done so much amazing predicting, and that predicting had then led to observable consequences that were totally consistent with what was written down in the mathematical models. So the story so far is that we have a strong force, and that packs quarks and stuff together into composite particles. We have an electroweak force, the W, the Z, and the photon, that is responsible, for example, electromagnetism, weak nuclear decays, and that interacts with both quarks and leptons. So in the standard model, we have this quark sector. This is the stuff that interacts via the strong force as well as the electroweak force. The lepton sector, which are electrons, their heavier cousins, and also these mysterious neutrino particles. And then we also have the force-carrying particles over here. And these are all tied together by symmetry. Do you have any questions at this point?
Top quark that you listed at the end of the discovery, this year is 30 years anniversary of the discovery. It was discovered here at Fermilab.
Yes. So I should have been a little bit better at putting these references in. This particle here, discovered at Fermilab. This particle, and any more. I know that this guy, and this guy were discovered here at Fermilab.
Fun fact is that all the quarks or fermions on the left side are discovered in the American, in the thing on this side of the Atlantic. On the other side, all the other particles are discovered in Europe.
Cool.
Except the electron, maybe. Electron is discovered in UK.
Yeah, Chadwick. Yeah. Any other questions?
So what's like the differentiating factor between a lepton and a quark, and can quarks like exist by themselves like leptons?
That's an excellent question. All right. So there's a slide in a little bit, but I'll tell you, what's the difference between an up and a charm quark, for example, is that they have the same charge, but this one is more massive than this. This one is more massive than this one, is more massive than this one. What happens in this top sector, these quarks interact via the strong force and the electroweak forces. These guys only interact via the electroweak forces. You'll notice we don't have electrons packed together in a nucleus. We have electrons on their own, right? So you can extend that to think about the lepton sector. So all these particles only interact via the electroweak force. Do we find quarks on our own? Now, the answer is no. And that ties back into our understanding of the force that binds them together. The strong nuclear force is so strong that if you try and pull two quarks apart from one another, there's so much energy there, and E equals mc squared, that it's going to create another pair of quarks. And then it's kind of like, you know, like when they say like cells divide, right, into other cells, you just end up with two other things, right? You can't break quarks together because of the strength of the strong force. So this quantum chromodynamical force is so strong that you actually can't separate an individual quark. And in the original proposal of the quark model, there was no guarantee that we would even see quarks. So the way that we actually observe them is we hit particles really, really strongly at a nucleus. And what we do then is we measure the underlying structure of the nucleon itself by looking at the different ways that particles scatter off that. So the discovery and observation of a quark was actually the discovery of the deep structure of a nucleon itself. It wasn't the individual observation.
So the particles in pink are responsible for the forces. Is it when they like interact with quarks and leptons that like they create force?
So you can think of them as kind of, if I was going to interact with, if I was going to, if I stand too close to a magnet, right, I feel something pulling me against the magnet because I've got metal jewelry. The thing that's pulling that is a field, right? But excitations in that field under the nature of particle physics, so the models that we use to understand this, we would call the photon. So the photon is a force carrier in the particle model. It's hard to kind of go into massive details about the ways that kind of works, but what you can imagine is under the particle model of physics, we don't just talk about the existence of fields, we kind of talk about something holding the hand of one thing and the other thing, and that's the strength of the force. It's like a magnet. Does that kind of make sense? I know it's very hard.
Yeah, I think so. So it's like the force between the, like for example, like a photon and another particle, and then third particle on the side.
Yeah.
Like it, like.
Yeah. Exactly.
Okay.
Yep.
So what is the difference between the strong force and the strong nuclear force? Because I was under the impression there's only one strong force.
No, this is a very good question, and this comes back to this question. So the way you can think of the strong nuclear force is like zooming out from the standard model to protons and neutrons. When it's fine to just treat things as protons and neutrons, the force that we observe around us, or around those protons and neutrons, really, we don't observe it here, is a strong nuclear force. But more fundamentally, once we talk about quarks and stuff, that's the strong force. So that's the quantum chromodynamics force. At that scale, you need to think of things in terms of the strong force. Once we're only talking about particles sticking together in larger structures, at that point we think of it as a strong nuclear force existing in the nuclei.
So I know that like photons are considered to be particles themselves. So are they also like made up of stuff like quarks and leptons, or are they considered elementary?
So so all the particles that I will show you in this are elementary particles in the standard model. Excellent. All right, so I only have a couple of slides left, and that's basically to tell you the final ingredient. And the final ingredient to the standard model is the Higgs particle. So what we did was we measured the existence of all these particles, and we were able to organize them into a table, essentially. And we were also able to say that there are forces that exchange that give us information about what's going on with the different interactions of particles. All right. It turns out the moment any of these particles has a mass, all of that breaks. Everything that we've structured breaks. All of those symmetries are no longer pretty anymore, because essentially there's something pulling those particles back from interacting in the way that we want them to. What helps is that if we give a mechanism that works together with that model, give the particles mass, then that restores everything that we were fine with before. We need a mechanism built into this model to explain how particles get their mass. Otherwise, the model is not sufficient. So what happened in 1964, together with a bunch of different researchers, Peter Higgs, proposed the existence of something called spontaneous symmetry breaking. That was the idea that we had to find a way of building in the breaking of different symmetries into the theory to keep it all consistent, to not ruin the symmetries and the model that we've constructed. To keep it all fine, he introduced this particular process. And this Higgs particle and this spontaneous symmetry is part of spontaneous symmetry breaking. And this is responsible for explaining, remember earlier I said we had a unification of electromagnetic and weak forces. Trying to understand how that unification works, we need spontaneous symmetry breaking. And also we need to understand how fundamental particles get their mass. So I'm not going to discuss information about electroweak theory because that is insane to try and get through in one slide. But what I will focus to you is how particles get their mass. So at this point, I haven't explained anything about the masses. We've measured particles, we've measured them with different masses, and we've used that to give information about potentially how composite or fundamental they might be. So we measure these particle masses extremely precisely using experiments as they have been developed. And what we do is we introduce the Higgs particle as part of the mechanism for giving a particle a mass. There are a number of different ways of thinking about this. One way of thinking about it that I like to think is probably a little bit more correct is when you shine a light at a prism. And many of you have done this just by playing around with the differently shaped glass in front of the window, right? If you have a if you have a light and it shines through a prism, different parts of that light will bend at different angles, and that will mean that they show up as a different color. You can kind of think of the Higgs particle as that prism. What happens is that other particles interact with the prism and they bend differently. What happens is that the Higgs particle has different interaction strengths with different particles in the standard model. Another way of thinking about it, which is more common in like the vernacular, especially after the Higgs mechanism and the Higgs particle received the Nobel Prize, was the idea of a cocktail party. So you can think of what happens is that a particle walks in the cocktail party and it's either extremely antisocial or it's really social. If it's a social person, particles, then it going from here to here is going to take way more time than if it's really antisocial. And what happens there is that the social score is essentially the mass, right? It moving from this point to this point will be easier or harder depending on the mass of the particle. And that interaction there is an interaction with the Higgs field and correspondingly with the Higgs particle. So what happens is that the Higgs allows, through its interactions, particles to have mass in a super consistent way with the rest of the particles in the standard model. Now, I'm not going to go into detail with this because you're about to have a discussion on collider physics, but the Higgs particle was proposed in '64 and it took until 2012 to discover the Higgs at CERN. So Peter Higgs was waiting a hell of a long time. And essentially what happened was that they looked at particle decays and they found the Higgs. And this was a triumph in particle physics and a really good example of what I said to you before about the scientific method. This model was proposed in '64 and they predicted the existence of this particle and they looked for it and they looked so hard and they found it. And that is extremely amazing. And this is also the point where I entered physics. I was doing my first year of undergraduate when they discovered the Higgs. So within like 4 months, I heard about this and I was like, damn, this is what I'm going to do. So I only have, how long left? No time left. So my next slide is just a conclusion slide. But I just want to tell you that we're still kept busy by these problems in the standard model already. So the standard model, right, does an exceedingly good job for generations, really. It has predicted the existence of things. We've gone out, we've measured them, and it's been consistent. So it's amazing. But there are things missing. There are a bunch of things missing. You should have said to me earlier, right, I wrote gravity on a slide earlier, and I've said nothing about gravity. Well, that's because the standard model says nothing about gravity. Gravity is not explained by the standard model. And there are many people who work on trying to bring gravity into a particle nature of matter. Dark matter. So dark matter is basically we stare up in the sky and we look at the way that particles, that matter interacts in astrophysical objects. And it says that there must be more matter there. There's more mass there than we can see. We can't see it, so it's dark. So there's dark stuff in the sky. We don't understand it. And in order to fully understand how we've gotten here as humans from the Big Bang to this point, we need extra matter there that we can't observe. So that's dark matter, and we don't know what it is. We don't know if it's a particle. We don't know if it's a force. We don't understand really all of the details of this yet. So that keeps us busy. Neutrinos, these particles along here keep us super busy, and this is a main area of my research, is that these particles don't interact with the Higgs. If they don't interact with the Higgs, they can't have a mass. But in 2015, the Nobel Prize was awarded for the discovery of neutrino masses. So neutrinos have a mass, but they don't interact with the Higgs in this model. So we need to basically say, how the hell do neutrinos get mass? We need to build models. We need to understand how these things interact with one another to basically explain what we're observing. Matter, antimatter, asymmetry, why are we all made of matter? I strategically did not tell you anything about antimatter. Essentially, all these particles exist and they're antiparticles. The antiparticles are exactly the same as these, but with opposite charges. So there's an electron, but there's also a positive guy called a positron. All of these things have antiparticles, and that's necessary in order to explain what's going on with the different interactions. And another thing that's really interesting to me is if I look at all the masses of these particles, I actually need an experimentalist to sit down and tell me the number for that mass. It's not entirely predicted by the model. So I have a bunch of numbers that I need to put in, about 27 numbers to make this math work. And we don't know why those numbers are the numbers they have. We don't understand why this guy is about 500 times heavier than that guy. Like, understanding those different mass structures, perhaps with underlying symmetry, is something called the standard model flavor puzzle. So flavors are the different types of these particles. We just call them flavors like an ice cream shop. So there's a whole bunch of different stuff that keep us busy now on trying to bring the standard model beyond and really, really get an understanding of the universe around us. So thank you.
Thank you, Inez. All right, we have time for a couple questions. There were some hands we couldn't get to last time.
So just a real quick question about the Higgs particle. Is it a field that you said, or was it a particle? And for like the cocktail party analogy, is it like the fundamental particle is like the popular or not popular guy that you're talking about?
So this is a very interesting question that brings me back to the fact that I'm trying not to talk about field theory. So essentially what happens is in field theory, you have a field, it exists. It's a mathematical object. And excitation in that field, so essentially, you know, when you play a guitar, there are certain notes that vibrate. Mathematically, it's the same physics, the same stuff that goes into understanding what an excitation is. An excitation in a field is what we call a particle in field theory. So a lot of these analogies work really well for, this is why I like the prism analogy instead of the cocktail party analogy, because in the cocktail party, we're saying that the room that you're walking through is the Higgs field. And you as the popular or unpopular person is the particle getting mass. Yeah, but then I have to introduce fields. So that's why I like the idea of just being like, there's a prism there, it's somewhere, and you just go in and there.
Any other questions? So, are the forces that you mentioned, are they distance dependent, like we observe gravity or electromagnetic?
Yes. So earlier before, when I was telling you the difference between a strong nuclear force and a strong force, at very, very, very short distances, a strong force is acting. The moment you move further away, you're only seeing the remnants of the strong force, which is the strong nuclear force. but you're not going to have gluons exchanged over a very large distance. The same thing, like gravity acts over extremely large distances. The weak force only acts over a very short distance. It's like 1 on 100, depending on your units, but it's a short distance. Like radioactive decay is only a very, it's not like I'm going to feel the actual decay process when I'm all the way over here. I might see the products, but I won't see the decay. Yeah.
So are these forces that you talked about, are they created like naturally? Are there like fields of those forces, or are those created by like the interaction of the particles?
I'm sorry, I didn't hear the last part of that before you said interactions of the particles.
Are the forces like, are they all their individual fields, like they're naturally occurring, or are they created by the interaction of their particles?
So it's sensible to think of them in both ways. This is this wild world of is light a particle or a wave or whatever. So there are ways of understanding them in the particle context and also in the field context. As I said earlier, a particle is kind of an excitation in the field. So you observe a particle, but the exchange of a particle corresponds to a field. Yeah. But all of them are basically that earlier statement about the existence of a symmetry, precluding the existence of a conservation law, actually precludes the existence of a force-carrying particle. Yeah.
All right, we're short on time. We're going to take a 4-minute break. If you have questions, feel free to come up and ask Ines during the break, or maybe you'll stick around for a bit. But we have to go on to let Martin talk. Got to hear about this beautiful machine called CMS. So we'll be back at 10, 12 people on Zoom. We're just going to get set up for the next speaker. And yeah, if you need to use the restroom or get some water, now is the time. Hello. I think we're going to transition into getting started again. So if the students could please take their seats. Thank you. All right. So up next, we have a talk on the Large Hadron Collider and the CMS experiment by Martin Kwok. Martin did his undergraduate study at the Chinese University of Hong Kong and got his PhD on the CMS experiment from Brown University in 2020, after which he spent 3 years at CERN. During that time, he spent 3 years at CERN during the LHC Run 2, which was from 2016 to 2018, and he helped with CMS's daily operation. And he has worked on multiple physics topics, such as searches for microscopic black holes, boosted Higgs bosons, and most recently, searches for long-lived exotic particles. So he works on CMS, and so after this, we will have a tour of CMS. So whenever you're ready, thank you, Martin. Take it away.
You me? Okay. Good. Turns out that I think I can shorten this talk by quite a bit because Ines did such an amazing job of introducing the standard model. It actually covers part of my topic. So I don't need to tell how they were formed. There's some bit of history of it. So I think what Ines told you was that tell us how we got here, and you have already seen a little bit glimpse of the history, that this history of discovering particle has everything to do with how we obtain these particles, and that's through a particle collider. And this is the only tool that we can make to study the smallest things. So if you remember, quantum mechanics tells us particles is roughly wave. So a particle with energy E will have a wavelength of lambda h bar c over E. What it means is that to be able to probe smaller inside the nucleus, you need higher, the smaller the scale that you want to probe, the higher energy you must be able to go. So that's why we want to go to higher energy. So all of these things that Ines talked about has a certain length scale. So atom is 10 to the minus 8 centimeters, and that corresponds to a certain energy that you need to reach in order to probe this scale. So if now there was a question of whether or not you can see an inside structure of an electron. Yes, that's a valid question to ask. But in order to probe that length scale, you have to go to higher energy, because I don't know if you know this, our human eye, the scale that you can see or detect is dictated by the wavelength. So if you're seeing a microscope, the limitation of light microscope, you cannot see under one wavelength of what the instrument that you're using. If you're using visible light, the length scale is about micrometer. Below which you cannot resolve it because it's shorter than the instrument that you use to see it. That's why if you need to see a better microscope, you use electrons, and you can accelerate them using the wave nature of the electrons. You can see more cell structures, and DNA you can probe inside up to at the atomic level. So in this sense, we push this idea to extreme. Then you get LHC, we'll be probing a very, very small, tiny scale, and that's how we can reveal the secret of the subatomic world. So this is actually taking from the start of the journey, happens roughly 100 years ago. This is a very rapid boom of science for the past century. And it started with 1991. Ernest Rutherford started a journey to probe subatomic structure with high energy particle. What he used is a decay of a heavy particle, radioactive decay, with energy of 5 mega electron volt. That gives us the length, probing the length scale of roughly the atomic nucleus of the atom scale. So 10 to the minus 10, 11 scale, 11 meter. So that was the first instrument. He did not need to accelerate. These energies just come from the nuclear interaction that you just saw. And the scale is roughly mega electron volt. This gives you a particle of 5% of speed of light, and is hitting a thin layer of gold foil of about 1,000 atom thick. What it reveals us is that our previous assumption of having uniform charge, negative and positive charge inside an atom was completely wrong. The atomic structure is actually more like very dense nucleus and 99% of empty space. That was very shocking, and that tells us that our theoretical assumption does not necessarily correspond to the nature. We need to build an experiment to see it. To capture how shocking this discovery was, in the quote of Rutherford, it was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it came back to hit you. So this is what he found. You shoot a particle with at 5% of light, speed of light, on 1,000 atom thick foil, and sometimes it bounces back, and it bounces back because the electric charge are so concentrated, and if you hit it, then it bounces back. So this is the beginning of the journey of understanding subatomic structure with high energy particles. So then you want to see smaller things. How do we get higher energy? Method 1, any guess? Yes, that's actually method 2, sorry. Method 1 was already revealed by Ines. So the immediate next step in the 1930s is we wait, because nature gives us free high energy particles all the time that cause cosmic ray. This is a picture that what Ines was referring to, their primary cosmic particle, predominantly proton, hitting our atmosphere with atoms, and then it produces secondary particles, and that leads to the discovery of muon, which you have already heard about. These, instead of MeV range, you have GeV range at the surface. It's one particle per centimeters per second. So you can just per minute, I think. So if you build a cloud chamber just in front of you, right here, right now, you will see particles shooting through this muon, shooting through you. Okay. So a bit of side note, human technology is nothing in front of the force of nature. These cosmic ray particle actually gets to incredibly high energy. So this is the rate of the particles. It spans like 20 orders of magnitude. I don't know if anything else has spent this kind of order of magnitude. And the x-axis is the energy range of the particle. So area C, which I'll talk about, is only here, and there's all the stuff that we can never dream of accelerating them that high. We observed, this is actually just last week, we observed in nature ultra high energy cosmic neutrino with 120 PeV. That's one particle 10,000 times higher than carrying 10,000 times larger energy than what we can create humanly. But there's a very important problem. But they're super, super rare. So it's one particle of such particle per kilometer square per century. So you have to build a kilometer square of detector and wait for a century, then you can have a chance of catching one of these. So this is, in terms of discovery, these are fascinating source of particle. Why they are, we are not even entirely sure how they can get to such high energy, but that's force of nature. But as an experimentalist, that's not necessarily what we want. We want something that can recreate. And method 2 is the best method we came up with, and that drives our discovery was the invention of accelerator. So you heard about 4 forces: gravity, weak, strong, and EM forces. Electromagnetism is the only force that human technology has mastered to manipulate and let this particle tell us something. So this is how the electromagnetic force interact with a charged particle. You don't have to understand the equation, except that besides having there's 2 terms. There's electric field that accelerate a charged particle. If you have a potential of V voltage, you apply a voltage across plate and then send a charged particle through it. There's an electric field in it. So think of it as a battery with 1.5 electron volt, 1.5 volt of a typical cell battery, and the electron passing through this gap will get an kinetic energy of 1.5 electron volt. So to get to the TeV scale that the RC is capable of doing, you will have to stack up these 10 to the 12 electron. This battery, it will be huge. It's not an easy task, but this is possible because electron can accelerate charged particle, electric field. And the second handle that we can have is magnetic field. Magnetic field bend charged particle, as we have seen. We cannot use it because it's always perpendicular to the motion of charged particle. We cannot use it to accelerate particle, but it can change the direction and change the direction of the charged particle. So then, if you want to have high energy and repeatable collisions, then you can come up with a concept like this. Oh, why don't we make the particle runs in circle with the help of magnetic field, and then gives them a kick every lap that it runs around. So it will be something like this. So a particle follows a circular trajectory if you give it a constant magnetic field. If you give it a magnetic field to bend it, so it runs around, and every time it comes around to electric field, then it gives you a kick, then gives you more energy. This paradigm is basically how the latest, greatest accelerator works. This is what we call synchrotron. So it's invented in 1944, so roughly 10 years after discovering cosmic ray. So this is a repeatable high-energy microscope. The latest one, with 40 years of technologies and many Nobel Prizes later, we arrived at RC, and now we are able to accelerate to an energy of 13 TeV tera electron volt, and that gives us down to the probe to 10 to the minus 17. This is the smallest length scale that human can probe right now. Okay, so Large Hadron Collider. Let's talk about the experiment, the machine, and then I'll talk about the experiment. So it's a circular proton-proton collider. Now you know why it's circular, because if you put in charged particle in a magnetic field, it runs in circle. And every time it crosses somewhere, it will get a kick from the electric field and then get extra high energy. Then you can gradually build up to 13 TeV or 6.5 TeV per beam of particle. So it's located not in here, in Europe. CERN is a European Center for Nuclear Research in France. So I never try to understand how CERN come to this term, but because it's French. Geneva is a French-speaking area. So it's an international physics in Geneva, Switzerland. They like to think about it is the collaboration is so international. They joke about that the E now is not stand for Europe, but everywhere. So this is the scale of the machine that we are having in order to get to this high energy is 27 kilometers in circumference. There is actually stranded across 2 nations. This is where CERN, the main site, is stranded across Switzerland and France, and CMS is actually all entirely in France. Geneva for thanks. Is it that? So me trying to get this microphone activated. Okay, I hope this is working. So we want not just high energy, but we want a lot of collisions so that we can we get a repeatable experiment. So the way we get a lot of collision is to have a lot of protons that collide together, not just colliding one particle, but we squeeze as much particle as we can in this circular orbit. So proton bunches circulate in 2 rings in the LHC using a very powerful magnet. This is many, many times stronger than the Earth magnetic field. And this is actually the limiting factor of the size of the collider, because we can only bend it so strong. So it circulates in opposite direction. There's 2 tunnels. The magnetic field goes in opposite direction, so then they goes into opposite direction. It has an incredibly high crossing rate, so 40 million times per second. Each bunch we managed to pack 10 to the 11 protons together in the bunches. So you can imagine how difficult it will be, because they are charged particles. They don't like each other. They try to repel, and we have all sorts of systems around the accelerator to keep this as inside a bunch. Each bunch will have 6.5 tera electron volt, and the collision energy, you collide 2 things together, 6.5 TeV and 6.5 TeV, you get 13 TeV in terms of center of mass energy. That is the amount of energy that you can use to create new particles and study what their interactions. So when the bunches cross parton, so you already heard about a proton not being the elementary particles. So there are inside proton, there's up quark, down quark, and strange quark, up quark and down quark, and a bunch of gluon inside. So this 6.5 TeV is not when you collide them together, the constituent of the proton does not carry the full energy of the proton. Only a fraction of them. It carries the constituent only carries the fraction of this energy, and they interact with each other. So what happens at the LHC collisions? How do we know? What do you mean by studying them? So quantum mechanics actually has a famous quote: anything not explicitly prohibited can happen in quantum mechanics. So what are the things that forbids any process to happen? That was what Ines discussed. Conservation law is what that prohibits. If anything is not protected or forbidden by conservation laws, anything can happen. So if you have 13 TeV of energy by the famous energy and mass equation from Einstein, you can create particle that weighs up to 13 TeV, minus the fact that your elementary, if your particles start with 13 TeV energy, okay, and this process, the standard model theory that you were taught in the last hour is not just a description; it's a mathematical model that gives us a predict what exactly particles can come out and how often they come out. So it's a very precise description of how what will happen when you smash proton and proton together. So this is how we accelerate this is only one side of the story when you produce where you are able to produce the particles. But to study them, we also need to detect them, and that's why the LC experiment comes from. It's hidden underground, 100-meter underground. This is the Geneva and Swiss and French border. This is the Alps. There's some cows, sweet and chocolate and cheese. But what we are interested in is 100-meter underground. There's 4 experiments here. Any guess of why we build the experiment underground? Yeah. That's one of the things. More?
Maybe lessen the chance of like particles from like the atmosphere interacting with it?
Exactly. That's precisely what it is. So you're putting your knowledge that you just learned together to shield from cosmic ray. We have 100 meters of rocks, solid rocks. We want our experiment to be only able to detect what we produce and not be interfered by the particle shower from what if you have a PeV electron, just neutrino just shooting at us. So we want to shield it from cosmic ray particles. So the first experiment, one of them is called Alice, or Alice, depending on what accent you pronounce it in. Study the collision of heavy ions, not protons. So this is a study of heavy nuclear particles and the study of the strong forces. And yeah, so they have a lower collision rate, but at this location. But the same tunnel can also not only accelerate proton, but heavy ions as well. And that by squeezing more nuclear particles and smash them together, you can better understand the nuclear forces that interaction happens there. So LCB is another experiment. It studies particles containing heavy quarks, and these quarks are produced very primarily in the forward direction. So it only catches one side, actually. If you have a look at this, it only catches one side of the particle. So these are specially designed detector to help us understand a particular type of particle called B hadron. That's why there's a LCB in it. That's the bottom quark. What I worked on is one of the 2 general purpose experiment called Atlas at the CERN site, and in the opposite side of the ring is the CMS experiment. So what does general purpose mean? General purpose means we study everything we can. We measure what we already know about very precisely. All the particles, we want to capture all the particles that comes out of the interaction so that we don't miss anything. We look for new things that we have never seen before, because anything can happen, will happen. It's like Murphy's Law. And that requirement is very stringent. It requires us to detect as many particles as possible, identify them correctly, and ultimately, we want to measure the energy and momentum precisely, because remember the neutrino influence, discovery of neutrino, it only happens if we can measure the energy, all the energy of the participating interaction correctly. So how many particles can we detect? So this is the standard model that you were taught. Any guess of how many particles we can detect with our detector? All of them? You are all correct and not so correct at the same time. We discovered them eventually, but we infer the existence of all of them from the experimental data, but what we can actually detect is just 3. because these are the only free particles that can travel long enough to be detected in our detector directly. That's what I meant. So electron is stable, that we know. Muon is what you have. It can travel through from atmosphere to down to Earth. And photon, of course, is a long-range force. Everything here is short range and very short-lived. So if you look for the collection of lists of particles that we have produced so far, we have documented more than 200 particle species by this particle data group hosted in Lawrence LBNL. Only 27 of them likely travel more than 1 micrometer. So this 200 plus particles is the particle zoo that we talked about. Only 27 of them can travel more than 1 micrometer. 1 micrometer is very tiny. If you require the distance to be 0.5 millimeter, only 13 of them. This kind of makes our life easier because we don't have to differentiate 200 of them. Our detector only need to be designed to detect this 13 particles. So you see here, these are the mesons. This is a top quark, W and Z boson and Higgs boson. The proper lifetime is 10 to the minus 23 seconds. So even if you're traveling at the speed of light, you wouldn't travel very far. So it won't make it to the detector directly. This is, cover most of the particle in the standard model. So how do we actually detect these particles? So we have anything that lives shorter than what you can build to detect will be, we can only detect the decay product of these particles. So you build layers of detectors and you detect the decay product of these short lifetime particles, and we have to infer the existence of the underlying particles. For medium lifetime, you can travel, the medium lifetime particles, it can travel a little bit and then decay. The stable particles will travel through the entire detector, and sometimes if it is a neutrino, we can also infer the existence of such stable particles. So in the standard model, there are very short lifetime, elementary, top, X, W, and Z. And there are medium lifetime. These are the interesting ones that leaves a slightly different signature, like the B meson, and tau, and K0 short. So these actually leaves a very different signature in our detector called Hadron and Jets. Remember, if you have a final state of, remember quarks and gluon do not like to be alone. Like what Ines talked about, you cannot separate them. There's no free quark that has ever been seen because of the what we call asymptotic freedom. You pull it hard enough, then more particles create out of the potential energy between the two quarks. So what we see in the experiment, if you ever have produced a, let's say, up quark in your final state of your proton collisions, what we observe in our detector is actually a spray of particle, collimated spray of particle in that direction. So you have a proton-proton collisions here. What you produce is a quark or gluon at the particle level, at the parton level, sorry. And what it goes through is something called hadronization, and it will give you that 13 list of particle at the end, and then this is what we actually capture, the hadrons. And as an experimentalist, it's a very difficult task because you are not detecting the whole particle directly, but you need to, again, infer from the collection of particles going in the same direction and try to infer the property, the energy and momentum of the underlying object. And this is what we call a jet. So jet means very different to differently to experimental physicists. And finally, the long-lived stable one. These are the particles that can be created and straightly be detected in a particle detector. So electron, muon, proton, photons. So these we can only detect stable particles. So there are 4 collections: hadrons, photons, electrons, and muons. When we design our detector, we just have to take care of consider these 4 collections of particles. These are the building blocks to reconstruct any type of particle we want to infer their existence and analyze the relationship between them. So how do we measure these particles? Let's try to design an HC experiment. So the number 1 criteria was we want to capture everything. To capture everything, you have to cover all possible angles. So that's what we meant by a hermetic detector. It's like playing Pokemon. You have got to catch them all. So there are thousands of particles that can be created at the collisions, and so the more particles you can capture, the better you can understand and explain what occurred during the collision. So a lot of them will have small energy depending on how much energy it gets from the collision. But what the interesting one will be the higher energy runs that comes out of the detector. So, and the second way, we want to measure the momentum of these particles. And again, electromagnetic force is the only thing that we know how to manipulate. So you bend these particles. If these are charged particles, the direction of the curvature will tells you the charge, because if you submerge this whole detector with a constant magnetic field, opposite charge particle will bend into a different direction. We know the direction of the B field, so if a charge particle bends in opposite direction, we know the sign of the charge, and the radius of curvature tells you the momentum. So if the momentum is if the trajectory is very curved, it means very low momentum. If it's almost straight, then it's a higher momentum. And a magnet that is cylindrical shape is called a solenoid. That's what the S stands for. Is in the CMS experiment is compact muon solenoid. We get to the solenoid part right now. So that means we need to measure the full trajectory of charged particle. And the way to do this is to build detector along the track. So that's why we have layers of detector capable of detecting as the charged particle move through your detector, it will release small signal, and then you can record the position that it hits. So this is what we call a tracker. We try to reconstruct the track of the particle in a magnetic field, so then we can measure the bending of the path of the trajectory and infer the momentum. Yep. So and what the detector is doing is try to connect the dots to create track. From the track we infer the momentum measurement. It has to be lightweight, because if instead of leaving energy in the detector the way you want it, it can interact and deflect. We don't want it to interact with the material of the detector. Instead, just leaving some tiny bit of amount of energy, enough for us to infer the momentum of the charged particle. So this is typically silicon semiconductor. They are very dense because you want to be able to distinguish if many tracks comes out of the collision. So we cover momentum. How do we measure energy? That's what we use. The technology we use is called calorimeters. So the way we do it is by using very dense material. So these calorimeter tends to comes after the tracker, because we need to destroy the particle, stop the particle, and see how hard it is to stop these particles in order to infer the energy. So it's what we call an absorber of energy to slow down. You can see this is a very dense material used in our electromagnetic calorimeter in CMS called lead tungstate. So an electron or photon will come in and initiate a shower like this. By capturing all the light coming out from this shower, we can infer the energy of the initial particle. So this is placed after the tracker because after this, we no longer see the particle, but we know the energy. And last but not least, remember the muon? These muon actually needs a special kind of detector to detect it because remember it can penetrate. It goes from the top of atmosphere to the Earth, and from the surface of the Earth down to sometimes down to our detector as well. So it has a very high penetration power. So we have to be built to detect high energy muons. It built a muon system at the outermost layer of the detector to capture them. So, but the way we do this is the same. We cannot use the silicon detector because we need to cover meter length of detector area. It's not at the center of the detector where we use the silicon detector. This is a much bigger volume, so we use different technology, but the principle is the same. We want to measure the track and infer the momentum of the particle. So that's what the muon comes in because we have a solenoid and it's compactly measuring these muon. And this is one of the best measurement that we have in CMS. So putting it all together as a different types of particles powerful through our detector, it goes like this. So muon, it goes from bending from one direction and the other direction, traveling all the way. This is a magnet in between the calorimeter and outermost muon system, providing the bending. So from this track, we can infer the momentum of the charged particle. If it's not charged, then it will be stopped by our hadronic calorimeter. That you can see the shower that creates here. If it's electron or photon, it will be stopped by electromagnetic calorimeter. And from the innermost tracker, any charged particle, we have a very highly granular detector that can reconstruct thousands of tracks coming out every 40 megahertz of collision. So this is a big detector, and the challenge does not stop at producing them. It stops. It's even we take way too much data to save it all. I have to speed up. Then produce 1 petabyte. All the detector gives 1 petabyte of data per second, and we have to keep 1% of 1% of these data to a few gigabytes per second. So this is even more than what you see 10 terabytes of data per user from TikTok or Instagram. So I want to quickly tell you a little bit on how we infer the existence of Higgs boson. So as I told you before, Higgs boson decays, and the standard model theory predicts precisely how the Higgs boson decay into different particles with certain probability or fraction of chance to these final states. The initial discovery in 2012 actually comes from the very rare, small fraction of these decays because our detectors are really good at measuring these decays products. So these are the photons and the Z boson or leptons coming from the Z bosons. And so we need to measure, for example, we take a Higgs to 2 photon interaction. So a Higgs will give up decay into 2 energy photons, like 0.2% of the time, you'll get 2 energy. We enforce conservation of energy and momentum in this in this decay, then from the energy of, if you measure the energy of these photons and the direction, the angle between them very well, then the photons from this Higgs decay, if they are coming from a Higgs, it will always come up to the mass of the Higgs boson. And that's how we can infer there's a Higgs particle coming from these photons. So if the photons truly comes from the decay, we should see these photons should resemble the Higgs particle's mass. Never perfect, because our detector isn't perfect. If you do not capture all of the particle, or sometimes you miss this particle, and that's our job as an experimentalist to measure this and correctly. So then, but you can imagine there's so many particles coming out. How do you know that you capture the correct photon? The answer is we don't. We count enough events that has these kind of two energetic photons, and what we observe in the presence of Higgs boson is an excess of what we expect without it. So it is, if you count all the events having two energetic photons in your detector, you have a distribution of number of events from, let's say, 110 and 150 GeV. The higher energy the photon, the less event you expect, because it's harder to produce high energy stuff. But if the photons are coming from the Higgs, it will always come up with the same place. So if you produce enough Higgs, you'll see a peak at the 125, telling you the mass of the Higgs boson. So, and this is what we see. This is the plot that as we accumulate data, we have a smooth falling background and a small bump here. And this is what we observed in 2012, and Peter Higgs won the Nobel Prize in 2013. So LC has a very rich physics program. It can study much more than just the Higgs, but you can imagine all the analysis that we do with the detector data is similar to what I described with the Higgs. Every one of these lines is one analysis of all CMS data to tell us about if you have extra dark matter surges that you can be able to produce at the LC, or the origins of the neutrino mass. There's some new particle that can account for the neutrino mass if they are within the reach of energy range of the LC. We can be able to say something about them. We are not just searching for new stuff. LC is also capable of very precise standard model measurements, and they can tell us if standard model is if there's any deviation from the standard model itself. And this is the latest, one of the latest measurement we published last week. CMS is able to measure the W boson mass, which is a very difficult measurement to very precise level. So what next happens to LC? We are very soon to undergo the high luminosity upgrade. Not just an energy that matters for a collider, but the amount of data is very important, because you want to see that little peak for very rare processes. So we are planning to collect more than 20 times of that data by 2040. We are improving our detector capability to be able to collect these events. And the mission is the same. We want to, now we have a precise probe to new physics from Higgs boson, and we can of course discover unknown particles. So in the pursuit of energy and intensity, how can we build more? You can ask, can we do better than LC more than 13 TeV? And the next collider may be a Muon one that's being proposed and very energetically received by our energy community, that we don't need to just restrict ourselves to proton. protons are composite particle. If we build a collider of 13 TeV, we ended up probing roughly 1 TeV. And because we are colliding only the constituents, taking a fraction of these energies are colliding. So if we, given the limitation of the magnet technology, we actually need 90 kilometers, which is a very big radius, even bigger than the RC, to reach 100 TeV. And we reach 100 TeV only to be able to produce particle of roughly 10 TeV. And that's the electroweak scale that we want, new energy frontier that we want to probe about. The reason why muon is interesting, muon is elementary. The energy you accelerate them, everything will convert to producing new particle. And it turns out that Fermilab sites can fit in a 10 TeV collider. And we're intensely thinking about this option right now and bring the energy frontier back to United States. I'll stop here. Any questions?
Thank you very much, Martin. I think we have time for maybe 1 or 2 questions.
Why does the LHC accelerate protons in the first place rather than anything else, like you started mentioning at the end?
That's a very good question. So if you look at this, there's 2 types of particle accelerator, hadrons or leptons. You notice the energy reached by a proton or hadron machine is factor of 10 or 100 more than we accelerate the lepton. And that is because something called synchrotron radiation. Unfortunately, this is not the only thing that happens when you accelerate a particle. So electromagnetism also tells you that if a charge is accelerating, it radiates energy. And that radiation is inversely proportional to the mass to the 4th power. That means if you a lighter particle will radiate much more energy than a heavier particle. So the options we can use is electrons or protons. Protons is 1,000 times, 2,000 times heavier than the electrons, so it radiates much less energy out. So imagine in this ring, every time you comes to the same place, it gives you a kick, right? But the particle is always accelerating when you turn them, and it loses energy on the way. So you cannot reach the same level of energy from accelerating an electron. And muon is actually the best of both worlds because you can still, because it's 200 times heavier than electrons, so it radiates much less energy, and we can reach higher energy to that of the electron colliders. Good question.
All right. One more, you think?
I was a bit confused when you just said if the particle loses acceleration as it's traveling in the circle part and only starts gaining acceleration in that little kick, what's the purpose in making the accelerator really large if we're trying to accelerate it a lot and it loses acceleration?
Yeah, so the amount of radiation gives off, that's a very good question. The amount of energy that you lose is inversely proportional to this radius. So by the acceleration is, the particle experiences a smaller acceleration and loses less energy if the radius is larger. That's also why actually only hadrons or hadron colliders are made in circular way in this for electron and linear collider. For electrons, we are colliding in a straight line to avoid this sort of synchrotron radiation.
All right, let's thank Martin again. And I want to thank both our speakers, Martin and Inez. And so we're going to transition over to the CMS virtual tour. So Zoltan, are you there?
Zoltan is here, and so am I. My name's Claire.
Excellent.
Yeah. We're just doing the splash screen at the moment, and then I will be able to see you all in a few seconds. Here we are. Yes. Hello. Everybody. Hi, Fermilab, and the online audience as well. Welcome to CECI, France, where we have 0.5 of the LHC, otherwise known as CMS experiment, which in my completely unbiased view is the absolute best experiment in the entire world. So my name is Claire Lee. I am a physicist. I work for Fermilab, but I live here so I can work on this experiment, helping keep the experiment running. Right now, we are shut down for maintenance and some repairs and things. We do this short shutdown over winter every year, just because it's necessary to help keep the machine and everything running in as optimal a way as possible. But also because in Europe, the electricity costs increase during the winter period. So this is the best time to do a shutdown if we have to do a shutdown at some point during the year. We will very soon be starting up again. So I am in the control room right now. This is the CMS control room, and it is staffed 24 hours a day, 7 days a week when we have the detector on. We will be starting to turn things back on as of the 3rd of March, and then you will have then you'll be able to see then there'll be people here all the time. For now, it's pretty quiet, it's pretty empty, and for those of us who do work in the operations, which can get really busy throughout the year, it's a nice time to just catch up on all of those things like documentation and stuff that nobody really likes to do, but you got to do. So yeah, so just to introduce myself, so my name is Claire. I'm actually a South African, and I came to CERN originally to work on the ATLAS experiment for my PhD, and then I did a short stint working on the Dune experiment in neutrinos before moving over to CMS. So feel free to put questions. For those of you on Zoom, please feel free to put questions in the chat, and I'll try and get to them. We will have my colleague Bugra. So Noemi is taking you on a tour of the control room right now, just so you can see what is. And there's Noemi over there. So hi, Noemi. My colleague, one of my colleagues will join us in a second and take you on the tour underground. So maybe I can actually say a little bit more about, I was just listening to those last questions that were asked. So one of the so there was a question about why do we smash protons together? And you can smash whatever you want. When you are doing a circular accelerator, as the speaker just said, accelerating electrons in a circle, you do end up losing a lot of energy. But the nice thing about smashing electrons together, for example, is that you get a very, very precise, very clean collision. So, you have like an electron and an anti-electron, and you can get a very, very nice clean electron, very specific. So you can set your machine to the energy of something like the energy of the Higgs boson, and then you can smash these together and make a lot of Higgs bosons. Why do we use protons? So protons are completely different. Protons, as you've heard, are made up of smaller particles called quarks. So a proton is like this little ball of quarks and gluons moving around all the time. And because of that, when the protons collide, it's the quarks or the gluon inside them that collide. Now, this gives us a whole bunch of different combinations. So this is what makes protons really useful as a discovery machine, because there's so many more ways of combining protons and quarks and gluons and things to create basically anything and everything, according to the laws of physics. So this makes protons really, really ideal to be used as a discovery machine which is why when we were looking for the Higgs boson and while we're looking for dark matter and microscopic black holes and all of these cool things, this is why we would want to use protons inside our accelerator. So, hi, we have people here with us. This is Bugra.
Last minute guy.
Hello, Bugra.
Hello.
So much.
It will be my pleasure to help you today.
So Bugra also works here on the online side. He's the run field manager, so he keeps us people who work on the detectors. He makes sure that we aren't running amok.
And then you are happy.
Yes, and we
that you have enough croissant and pain chocolat in the morning to.
Very important. They bring us
important part of
pain
the
chocolat.
RFM.
Probably the most important
Human
part
efficiency
is
factor.
to feed the shifters.
So I will be going down with Noemi.
Amazing. We will see you guys down there. Great. Thank you.
Bye. See you soon. Thank you.
Also, to the room, if there are questions as we go, because we're going to be walking around, there's a lot to see. So if you do have questions, feel free to ask them at any moment, and we'll be very, very happy to answer. You don't have to wait until the end to answer your question.
Sounds good. You can hear me? You can hear us?
Yes, we can hear you perfectly.
Cool.
Great.
We'll pop in if we have questions.
All right. So excellent. So let's see. So this is another very important part. This is the sort of coffee station vending machine. The shifts, we have 3 shifts a day. The first shift starts at 7 a.m. and goes to 3 p.m. Then there's a 3 p.m. to 11 p.m. shift, and then there's the night shift, the graveyard shift, the owl shift, whatever you want to call it, which goes from 11 p.m. to 7 a.m. in the morning. So that one, coffee is really important. We have numerous coffee machines in various places around here. So yeah, they are walking right now. Okay, we may lose signal as we're moving through the building, but you'll soon see we'll take you to the first door, the first personnel access door, which will allow us to access underground. Here at CERN, the access system is based on we restrict access in, but then once you're in case of an emergency, you are able to get out without having to scan a card or a dosimeter or anything. So here's Bugra. Tell us what you're up to.
That's exactly what you were talking about. So to enter in, I need to batch with my dosimeter, and I have my biometry information here, and that will be matched with my retina, with the retina scan. So, and then voila, I see the green light, so I can go in. And on the way out, if there is an emergency, as Claire was saying, there is a handle that I can break, and I can go out without the need to batch, and yeah, back to safety. And when Noemi is trying to come in, you have to be really careful. There is a sensor that doesn't want you to have more people in the box at the same time. So you have to really enter with one step at a time with all the materials.
It's very sensitive, so it's really designed.
It is very sensitive.
You can't sneak someone in with you. It checks that you're not bringing equipment in or out. Sometimes if I wear a long skirt, that's enough to just trigger the sensors because it thinks I'm sneaking something.
Exactly, and then you are out. You have to restart. Exactly. So we are going to take the elevator now that will bring us 97 meters down into the Earth, where the ground floor of the LHC and the CMS experiment is. Unfortunately, we will lose the signal here, so you will lose us at some point. But until the moment that you lose us, please enjoy the image of the height of the elevator. See you soon.
Thanks. Yeah, so you may have seen we only have 3 buttons on the lift. There's -1, -2, -3, and we're going all the way down to -3. -3 is the floor of the cavern, which is about 97 meters underground. The second floor is only like about 10 meters above that, and that is level with the LHC itself. And then -1 is just another 10 or so meters above that. You can see the counter as it goes. The lift goes pretty fast. And actually, here at the LHC, you know how normally they say do not take the elevator in case of fire. Here at all of the LHC experiments, the lift shafts are in a fireproof area that's held under positive pressure. So it is actually the safest place to be if there is a fire. So here we are at -3.
Yep, welcome to the ground floor. We will do the same thing. I will pass the camera to Noemi, and I will use my access system. And now I need to be also in the access rights for the experimental cavern. There are 2 different partitions in CMS. So when there is collisions inside, we can still come to the service cavern, but we cannot go to the experimental cavern, whereas we are in the end of year shutdown, so we can access the experiment. So you will have the pleasure to see our beautiful experiment almost closed. I'm giving you some teasers, but you will see it. So let's wait for Noemi also to pass, hopefully in one shot this time.
You may have noticed these doors are different colors, and that's for the different regions. So the yellow doors take you through into the experimental zones, which do get radiation during the visit, during just the normal running of the LHC. But people, you know, we have a special team of radiation protection people who will go and do a sweep of the cavern to make sure that it's safe for us to enter at the start of the end shutdown. And
so this is the long tunnel that I love to walk every time I'm doing this visit.
Dum 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 dum.
Yeah, exactly. I want to measure my heartbeat here. It's probably reaching 120. I am burning some calories here.
It's always
Yes.
exciting.
Voila, please enjoy the view.
Welcome to CMS.
I mean, it's almost closed. So on this side, it's completely closed actually. So you can see the cap. You can see the metal cover that isolates everything within the heart of the detector. And you can see the forward calorimeters and their shielding and the support that is already in place on this side. On the other side, we can still see some muon chambers, but on this side, on this side we are ready for the collisions basically.
Bugra, can you go and stand there next to the end cap there so that we can see just the scale,
the size difference.
See the size of the.
I am 1.73 meters, just to give you.
There we go.
A precise measure.
So yeah, that's we are about 15 meters.
15 meters, exactly.
From top to bottom.
Exactly, and then 25 meters, I think, in the length.
Yeah. So on the screen here is where we're showing also a schematic diagram of the experiment. So you're able to see this orangey yellow shielding that Bugra pointed out, and then this red circle, which is the end part of the iron of the steel return yoke. So you may have heard that CMS is built in slices. So you know, you can sort of imagine like you take a Swiss roll or something, and then we've sliced it up into 15 different slices. And each slice has a bunch of different layers or something that can tell us that can help us detect the different types of particles. What are we looking at right now? What are we looking at right now?
Sorry, I couldn't unmute. Sorry.
No
yes. So we are almost in the center of the detector. Basically, we are in the center of the barrel, I would say. Is this a slice of the magnet? I think this is a slice of the magnet. And yeah, I will give it back to you, Noemi, because I cannot handle this camera. It's too technical for me to keep it and talk at the same time. So you can see a lot of cables that is coming in. So the data that comes from all the 17 million channels that we have, maybe 20 million channels, that is sent to the service cavern through three different passage points between the 2 caverns that goes under the structure, under the floor, and enters to the service cavern, where the very first selection and analysis of the data is done. we have 40 million bunch crossings per second, but we cannot store all of them. So we have to decide now until HLA3, 100,000-ish out of it at the level 1 with the hardware trigger on the other side, and then send it to the surface, and there we reduce to about 1,000 or 2,000 events per second, and that's enough for our physics code to do all the searches and measurements that we are doing. Voila, that's how the data is flowing and how the experiment is also controlled. All these cables are also doing the monitoring of the experiment, making sure that the cooling is working fine, the detector conditions are fine, the sensors are alive, and we don't have any issues that can cause problems in the operation of the detector. We have several layers of detectors, as Claire was already mentioning. It's of course within this range. Maybe we can continue walking, and then you will see at least the end cap muon system, which is the outermost layer of the muon system.
So
and
I had a quick question.
Sure.
So I feel like we've done this virtual tour before, but we've never gotten to go in and see the detector like this. Is this because of that you're doing maintenance right now that we're able to get this exclusive access? And I guess maybe you could point out where the beam line is, just so the students can appreciate.
You can see the beam line now here. The orange that becomes aluminum foil on the left, that's the beam pipe, basically. So here on this side, we are still open. Are we a plus or minus here? I always forget.
That's minus. That's minus.
We are on the minus, yes.
Yeah.
So on the minus side, the operation is still not over. 1 hour before, there was still some team working on the end cap muon system. So the question was about how we can access now. I'm sorry, I didn't get the question completely. Maybe Claire can answer.
Sure, yeah. So if you've done a tour before, or even if you come here in person, we can take you into the cabin.
But
and
only to the balcony.
Yeah, there's a special balcony that's reserved for visitors. So what you guys are seeing today is parts that we're able to take you virtually that we would never be able to take any public person if they came to visit. So like walking on the floor here, looking up, you see that big tube going up, that goes up to the surface. That is 100 meters and that goes up to the surface, and that is the shaft where the slices of CMS were lowered.
Yes, exactly. All the experiment was lowered down one by one with a very delicate operation, because you can see the clearance between the end of the shaft, the wall of the shaft, and the experimental material is about 10, 12 centimeters from each side. So it took 12 to 15 hours, I think, for each slice to go down. To make sure that there was no pendulum-like motion, that was to avoid the experiment to hit the wall of the shaft, etc. It was a very delicate operation, and I was not here back then, and I am happy about it.
Yeah, these are one-of-a-kind pieces, and like even first of all, you can't insure them because it's one-of-a-kind, hand-built by thousands of people around the world. And also hundreds, like thousands of person power hours. So if it does break, even if you could convince somebody to give you the money to build another one, it would still take a long time.
You would still need the person power, exactly.
Yeah.
That costs probably more than the material itself.
I think a lot of people just really held their breath when those pieces, those slices were being lowered.
Let's do some magic.
Oh yeah, no.
We don't have magnetic field anymore. Obviously, the magnet is off because there is the maintenance. But in the corners of the in the sharp places of the feet, you can see that there's still a magnetic field that is remaining. So with the chain of attaches, you can see that it sticks on the wall. You can even build a Christmas tree. That's what they did back then, in the shape of a tree. I cannot do it. I am not that of an artist, but yes.
Yeah, so we have a solenoid magnet, and when we turn it on, it takes 18,000 amps of current. It's obviously a super cooled magnet, so we cool it with liquid helium, and then that provides us with a 3.8 Tesla magnetic field, which helps us bend the particles And that allows us to tell which charge different particles have, because different, like a positively charged particle will bend the opposite direction to a negatively charged particle. And it also allows us to calculate the momentum very accurately by plotting the curvature of the path. So this is really nice. You can see the beam pipe so beautifully here. And if you've seen a cross section of the LHC magnets, there are actually, for most of the way around the LHC ring, there are two separate beam pipes. They're only about like a centimeter or so in diameter. The entire thing has to be under a really, really good vacuum so that the protons don't bump into anything as they're traveling. But so they're going in two separate beam pipes for most of the way around. But just on the outside of each of the big detectors, those beam pipes merge into one beam pipe, and that's what you see there. So it's a very fragile tube made of beryllium. I think there's a strap in between one of these slices. There's a strap kind of supporting it so that it doesn't sag or anything. And that's where the protons travel. What are these big pizza wedges thingies that we're looking at over here in front of us, Bugra?
Which one are you asking about?
The wheel, the Muon wheel. Maybe you can.
So it's as I said already while walking here, this is the last piece of the detector material that you can see today, because this part is still open. This is the part of the end cap Muon system. It's for the RPC. R stands for RPC. So end cap -4 sector 3. I don't know I don't remember the numbering, but each chamber has its own address. So they are there to measure the muons basically. And Noemi.
Yeah, the 4 one is.
So the 4 is the new layer that is brand new added.
Cool.
Yeah, the ring that is the innermost ring is a new addition to our RPC detector that I learned just now.
These are actual. This is actual detector pieces. Oh, you can see another person walking on the opposite side there as well to get a sense of scale. So each of these panels is a specialized detector, and their job is basically to detect muons.
Yes.
Because
yeah.
No, go for it.
No, I was just please finish, and I will take for the movement of the detectors.
Oh, actually, yeah. Let's talk about that. That's really interesting.
So you see, we have orange stuff here. These are feet with pressurized air inside, so it can literally lift the detector off the ground, such that we can really slide it without much friction left. So it's really, I mean, it's not easy still, but it's easier to move it to separate the slices. So it takes, I think, full 2 weeks to reach the heart of the detector, more or less, and 2 weeks to close it. So we are almost closed. We have, I think, 2 slices to move. This guy should move a little bit to the left still, maybe. There is still a little bit of opening left, as you can see. So in the normal operating conditions, it will be really brought together. You can see the support for the beam pipe that comes from the top, not to put any mechanical stress on the beam pipe and make sure that it's not breaking. That's only when we open the slices apart. And then this cap, this protection layer will also come, and it will close, and it will confine the magnetic field within the volume, and it will make sure that everything is shielded and ready for operation. There is an interesting thing that I learned today as well, and I want to talk about. There is a robot arm. Okay, then I will talk about it in 5 minutes.
Okay.
Back to you, Claire.
All right. So another really important thing that we need to think about when moving these slices is it's actually not even as easy as you think. So the entire Large Hadron Collider itself, the 27-kilometer, 16-mile long tunnel, when they built the tunnel, the only way they could fit the tunnel in between the lake on the one side and this mountain range on the other side meant that it had to be tilted slightly. So the the LHC is tilted by about 1.4 degrees. Now our detector has to be perfectly perpendicular to the beam pipe to make sure that we get the most accurate measurements, which means that our 14,000 ton detector is also sitting at an angle of about 1.4 degrees. And so when we're moving slices backwards and forwards, this is another thing that we have to pay attention to, is the slight angle that the whole thing is sitting at.
So
What's here?
let me put a parenthesis here. This is the new stuff that I learned. Every time I do this visit, I learn something, and I love it.
Same.
So I am in a remote operation point for a robot that is situated like few meters, maybe 10 meters, 5 meters in front of me, that is doing a very delicate operation. It's drilling through the shielding, the radiation shielding, but it's radioactive. There is still remnant radiation there. So a person cannot operate this. So there is a robot that is operated from here that does the job, and it's I think it's cool.
That is really, really cool. Yeah. I was watching, actually, there was a sort of crane moving the robot from the one side of the cavern to the other side of the cavern the other day. So it's like really cool now to see it actually parked in place, and so this shielding, this orange shielding, wraps around the beam pipe to protect our detector. Yeah, so to protect our detector from the radiation produced by the beam.
Yeah, exactly. That's the purpose of it. It just really surrounds the beam pipe and the detector material that you still have closer to the beam pipe, outside the central CMS, basically.
That's cool.
And with that, I have the chance to walk around the detector.
Now we're on the top, or close
Almost.
to the top. Almost at the top.
We have maybe one floor left.
Amazing.
We will be there. We will be there. Don't worry. We go there as well. That's triggering a little bit of height fright for me, but I'm getting rid of it.
Another thing that's coming up for us is, once we've closed up all the slices and we're ready to close and seal the cavern, we have to do a thorough cleaning of the cavern, because people have been working the whole time. Tiny little screws or nuts or bolts might have fallen down just as people walk. And if we turn on our magnet again after that, and it catches one of these, it could rip through the detector and do a lot of damage. So we have a day where a whole bunch of us get kitted up in suit, like cleaning stuff, and we go with alcohol, cleaning alcohol, and cloths, and vacuum cleaners that go on our back, so you feel like a bit of a ghostbuster. I never vacuum at home. I hate vacuuming, but that's the one time that I will vacuum.
And the magnetic brush.
And the magnetic brush, so that we can, any tiny little filaments or anything that have been left. And also,
that can move. Yeah.
Because that shaft is up open to the surface, we also quite often find dead mice who have managed to fall down. And you find a dead crusty mouse as well. So it's kind of fun. But yeah, you got to do a good spring clean on your detector as well.
Yeah, before you operate it.
Yeah.
At high magnetic fields. Exactly. Interesting stories. Okay, we are climbing up.
Yeah. So yeah, again, this is all of the stuff that you would never see if you came here in person. So you're getting a very, very cool
not even for a normal CMS citizen, you wouldn't be ending up here.
Exactly. Yeah.
It's not only for visitors, also for the guides that has this privilege. I am encouraging you guys to become guides as well at some point.
Yes, I am a guide. It's fun.
Okay, we are almost on the top of the detector, guys.
Cool. So, here's another fun fact. So, we've had to dig out a big cavern to put our detector in, and this cavern is essentially a big underground air bubble. Now, there's 4 of these big caverns around the LHC, and CMS CMS is 14,000 tons. It's the heaviest detector. So we're actually not moving inside our air bubble, but the other detectors are not as heavy as us, and their caverns, their big cavernous air bubbles, are actually rising
Floating,
slowly to the surface. It's like, you know, like when you create an air bubble at the bottom of the swimming pool and it goes up. That is what's happening. It's a couple of centimeters that it has moved since 2006, but it's noticeable. And at some point, they even have to adjust the LHC beam and the magnets to account for the fact that they're floating up. So one day, at some point in the future, the LHC is going to pop up to the surface.
It will take some time for that, but okay. Shall we talk about this nice fire extinguishing system that we have as the very last option?
Yeah, sure.
You see,
So there was just one question. I see somebody asked how tall the detector is. So we mentioned this. It's 15 meters from
Right.
the bottom to the top. So Bugra is standing 15
On top
meters
of
above the ground right now.
yes, 15 meters plus 1.73.
Yeah.
So these red nozzles are just for dumping in foam in case of fire that we cannot control with other means. So this is the very last option. So it would fill up all the cavern with soap foam, basically, that would stick to the surface of the detector material, everything that you see here, and that would cut the oxygen to the fire and seize the fire. Yeah, it was tested before the experiment was here. We have cool pictures of CMS cavern, like a foam party, but it was never used again. That we are happy that it was never used again after that.
How long does it take to fill up the entire cavern with
I knew
foam?
1
Do you
hour, but
know?
is it true? Maybe Zoltan can tell.
Couple of minutes.
It's a few.
Even couple of minutes. Yeah,
Couple of
it has to
minutes.
be fast. Yes. To fill up completely, like really, like all foam. Okay.
Yep.
But,
The fun fact is that you can still walk inside. Of
Yeah, sure. I mean,
you can still breathe.
there's still air in it.
Yep.
And you have the helium tank, right? This is the cooling.
The Jure, yeah.
And the small one that feeds the magnet, and it's not. Are we cool now? Is it active? It's not active yet, right?
No. We'll
We
only
wouldn't be here, right?
yeah,
There is
that'll
no
only
active
be in
cooling.
like 25th of March that they'll have the.
And we are about 30, 40 Kelvin now. What is the temperature? That should be something like that.
Let me check.
We can have a look on the screen.
On CMS Online, yeah.
Yeah.
Or you are in the control room.
Yeah. Zoltan's just going to have a look on the one screen for the magnet temperature.
That's the big, and here it is the big helium tank for the cooling. It's written helium.
Just in case we forget.
Just in case that you forget, yes.
Yeah, and that's the reservoir, right, as well. So we've got the helium that's in the thing, and then also spares to make sure that it can keep running. Because the problem with the thing about a superconducting magnet is that you have to keep it cold, because as soon as it stops being cold, then you get resistance, and then the thing heats up, and that's what's called a quench, which can actually be
And
very
you have
bad.
18,000 amperes of current, which is not a simple thing.
Very unpleasant for the magnet, and very unpleasant for everyone.
for the cooling systems as well, it can be. So you have to really dump the current as fast as possible. Release the gas as fast.
14.
14.
14
14.
Kelvin.
Okay.
Okay, so it's pretty cold.
So
cool still.
3 months no cooling, 14 Kelvin from 5 Kelvin. That's quite efficient isolation.
Yeah.
But the vacuum is there still, right? The vacuum never stops.
The beam vacuum, the beam vacuum does the beam vacuum won't stop during the year-end stop.
Okay.
So that's why for the audience, the beam pipe the entire way around the LHC is held under a vacuum. Now the LHC does come in segments, so if you do really need to work on a segment, you can close it off, and you just take you can, so like if we needed to take this beam pipe open, they could do that, but
Yeah.
it does also take quite a long time. Once you put everything back, it takes quite a lot of time, maybe a couple of months, I think, to sort of get the vacuum out. And this happens in a few stages. So they like suck as much as possible, and then they have what's called a bake out, where they heat it up to give the particles a bit more energy, and then they're able to suck out some more. So it's quite a process. So
Yeah,
not
it's
one you
quite
want
an
to
operation.
do.
Yeah, we
Yeah.
had this situation in 2022, I think, for one sector, but
Yeah,
hopefully
that's right.
we could continue the operations.
So you're at the visitors balcony
Visitor
now.
balcony, yes. This would have been the maximum you would have seen as a normal visitor. I was here 1 hour ago for a normal visit, for an in-person visit, and it was still quite fun, but not as fun as the virtual visit, I must
It's
I
still a
must say.
lovely view. What's that big tank on at the end of the platform over there?
The big tank on the platform. Which platform and
the
which
end,
tank?
like so if you look to where we're looking right now, if you look to the left,
To the left, yes.
there's a big tank over there.
Is it the cooling? I don't. Yes, the gray
Yeah.
one. It's
Yeah.
for the cooling. Yes.
I think that's the cooling for the tracker, right? I think.
Is it our SS1 or SS2?
I think
No, the SS1, SS2 are one level below.
On the other side. Right. Yeah.
Yeah.
See, there's so much stuff that like even
C6F14, that's tracker.
That's tracker. Yeah,
For tracker, yes.
Yeah, the C6F14.
Yeah.
Yeah. So it's one of the two. Yeah.
Yes,
So
one of the two cooling. Yeah.
there's
Cool,
so
huh?
much that goes into building a detector. It's not just about the physics. There's engineering. If you
You can
really
see all the
really like cabling.
all the
You-
all the copper cooling stuff, everything,
You
all
were
the cameras that we have in the detector to localize it as well for visual alignment and a lot of stuff that goes inside.
You were
And,
mentioning earlier about the readout channels. So just for data readout, we have 120 million
120,
readout
yes,
channels.
yes.
And the pixel detector has more than half of
Itself.
those.
Yep,
66 million
exactly.
per pixel.
Mm-hmm. Thanks for the numbers. I'm bad in number remembering.
I'm also not so great, but I'm lucky because I'm sitting here with a picture right next to me. I've got all the numbers.
That you don't have to memorize.
No.
I was just 1 order of magnitude away from the correctness. So,
Yeah,
it's
okay.
what's
What's 1 order of magnitude amongst friends?
It's just. Okay, thanks.
Yeah, if you're an astrophysicist, then 10, 20, 100 orders of magnitude, that doesn't matter. So, 1 order of magnitude, I think is pretty good. Yeah, so what, you guys are coming back up now. So I'm sure that we have some questions in the room.
Yes, we can stay for the questions if you like for 5 more minutes.
Sure.
We can stay as long as you guys want.
And then slowly we will move up.
Do we have any questions in the room? Don't be shy, people.
Yes, one's coming.
So the LHC is a proton-proton collider. How do you isolate the protons from the other parts of an atom?
Oh, that's a great question. It's actually kind of easy because we just start with a little tank of hydrogen gas. And I mean like a little tank like this, which will last us years. Hydrogen is 1 proton with 1 electron. So effectively, all you have to do is get rid of that electron and you are left with the protons. In practice, it's a little bit more technical. So what they actually do is so you can't move a neutral particle with an electric or a magnetic field. Doesn't do anything. So what we first do is we take the hydrogen and then they add an electron on, so it makes it a negative ion. And then that allows it to start moving down, and then they strip the 2 electrons off and send the proton down the linear accelerator. This is the new linear accelerator that's just started. We've just started using in the last couple of years. Yeah, so that's it. That's how we get the protons. One interesting thing about the LHC is that they use protons in both beams. At Fermilab, the Fermilab used to have the world's highest energy accelerator called the Tevatron, and that had a proton antiproton beam. Now, antiprotons are harder to get than protons, but if you think about the magnets that you need to get the protons and the going around in a circle, if you have a proton going in one direction, that is the same as an antiproton going in the opposite direction. You can have the same force on both of them to make them bend around in the circle that you want. So the magnets for the Tevatron just needed like one magnetic field that could work on both the protons and the antiprotons to make them go around in the circle. The LHC uses protons.
Similarly for LEP. For the LEP, it was the same
Similarly
case.
for LEP, exactly. Yeah. The LHC uses protons going in, but now a proton going in this direction is going to be opposite. You're going to need an opposite force to a proton going in the opposite direction, which means that the magnetic field inside the LHC magnet is a lot more complicated. You have to have, like, in one magnet, you have to have two magnetic fields, you know, pushing the particles in opposite directions. So, you know, in one case, it's easier to get the particles, but then your magnetic field is more complicated. So these are all things that you have to think of.
So we can say goodbye to the experimental cavern, and we will move to the service cavern.
Cool, thanks. Bugra, we have a question from the Zoom who asks,
yes.
How long did it take to build the detector?
Ooh, 10 years, I would say, in total, from the day one to making it ready, right?
And that's day one, just from the start of building. There was an extra 10, 15 years of planning that went into it, right?
I don't know when exactly the building on the surface started.
Interest was submitted in 1993.
So Zoltan is mentioning the letter of intent, which is when the physicists get together for the first time and submit a document saying, this is a detector we would like to build. That was submitted in 1993. The caverns started being excavated, I think, in around 2000. And that process, it was a process. First of all, they started digging down, and then we discovered some ancient Roman ruins. So we had to get a team of archaeologists in to check that out. Then we dug down some more, and there's an underground river here. So we had to freeze the river and then tunnel through the frozen water and quickly patch it up with concrete behind us as we went. And then we got down, and the ground here is really soft. So like if you've ever been to a beach and you're trying to dig two holes next to each other, you have to like do some really good reinforcing in between. So as we were digging the caverns, we would reinforce everything. So that took a while. And then the LHC started in, like, with its first protons inside the LHC was in 2008. So from 1993 to 2008, that seems like quite a long time. Well, it is a long time for planning an experiment. So Bugra, so remember I said you're digging two caverns. So one is the cavern that holds the detector, and anything
the other
that
one.
Yeah, sorry. And the other one is where we are now with Bugra.
Exactly. So we have the gas room that serves a lot of material to the experiment. You can see a lot of pipes that goes from here to either to gaseous detectors, or for us, for tracker, we have also here, I think, some racks. It was in this row, if I recall correctly. Yes, these are for us as well. Mm-hmm. Sorry, I say us because we are a part of tracker, and it doesn't mean I don't like the others. It's just that I'm working for them as well. And same for Claire.
Yeah.
So yes, you have a lot of control valves and everything that is remotely controlled as well. That the flows are for RPC, for the detecting material, I presume, and also for cooling. So here we have obviously a risk of oxygen deficiency, and if there are oxygen sensors in this room, and if one of them measures a level that is below 19%, it will just lit up here, and we would know that there is danger, there is a lack of oxygen, and we should go back to safety. 19% is still enough that you can survive. It's above the lethal range, but it gives you enough time to escape. And if you are in the cavern, or if you are working on a crane, you need to wear a mask, as my colleague is always doing here. You open this little box, self-rescue mask, and you unfold a bag that contains a potassium mixture inside that converts the carbon dioxide to oxygen. It's a closed circuit reaction. It's an exothermic reaction, so you have to really protect yourself. It gets hot, and you have to close your nose, that the circuit is closed, and you can breathe for enough time for going out. And you have goggles that comes in as well to protect your eyes from either smoke or whatever gas that is released that causes the evacuation alarm. So with that, we can move through the racks, and the word is yours, Claire.
Sure. So the first set of these racks, well, a part of these racks handle this huge amount of data flow that comes out of the detector. And one way to think about it is just with 65 protons colliding every 25 nanoseconds inside our detector. There we go, it's the trigger and DAC. We have so much information coming out of the detector that we physically cannot store all of this information. So we have to make guesses based on what we think. Like every 25 nanoseconds, we have to guess, this looks like an interesting event. And it's sort of equivalent of, imagine standing in front of a big waterfall and you're holding a cup. And as the waterfall is going, you can take a cup of water out at a time. That is how much data we're able to save compared to how much data we're getting from the LHC. So that is what the trigger and the data acquisition system does, because otherwise we will just saturate our storage, and then we won't get anything.
So this is your last glimpse to the CMS experiment between the USC and the UXC, the service and the experimental caverns. We have 10 meters of concrete block and 7, sorry. As I said, I'm bad with numbers. So there is a sliding door of a concrete block that separates the two. And when we have access times, we need to bring down material through this small shaft and put it in. So we have this point as well. We can, I mean, we shouldn't walk in from there because it's a different security partition, but still you can have a last glimpse on the detector. And this part is still in USC, right?
Yeah, you're still in USC.
And it's downstairs.
So this the 7 meters of concrete is a result of the ground here being soft. So they had to reinforce with extra concrete. If you go to the Atlas experiment, for example, the ground there is very rocky. They didn't need to build this extra concrete. However, to perfectly shield yourself from the radiation produced by the LHC, you need 7 meters of concrete. So what this actually means is that the CMS detector, this area here, the service cavern, we can bring visitors to even when the LHC is running, because it's completely radiation-free, completely declassified. And we are the only experiment that allows us to bring visitors underground while the detector is running, and also the only experiment that allows kids to visit the experimental cavern during these shutdown periods. So that's, thanks, Soft Ground. That's very nice of you. We have one question about how they transported the parts to CERN. And this is another really, really interesting thing to think about. So we have this detector that is built of thousands, millions of pieces. And they were built all around the world. Different laboratories contributed different things all around the world. And what actually, and then they shipped them here to CERN. And in some cases, they flew into the Geneva airport and then were brought to CERN on a truck. In other cases, they were brought by land, like over the mountain and stuff. So, and then they all came here 2.5, and we built the detector on the surface in these slices, and then piece by piece lowered the slices down. This is one very, very small piece, not even an entire full slice, because that takes up the entire width of the shaft there. But that is so yeah, just like if you're into logistics and planning and transport and stuff, this is another huge big job. We have spreadsheets and that are like this big just to plan the arrival, and also you need to build the detector from the inside. Well, when you're building it together, the inside has to be ready before the outside. So if you have some delays on the inside bits, then that affects everything. So it's just like a really, really intense and complicated, but also kind of fun experience of putting together this really massive piece of equipment. Yeah. Do we have any other questions in the room?
No other questions?
No other questions.
Anyone?
Another interesting picture.
You found an interesting. Oh, that's a lovely picture of one of the slices being lowered down. There, look at that is one of the slices being lowered down, and if you look closely, you can see that there's only like 10 centimeters or so on the other side. Somebody here in the control room has a question for us. He wants to know how much electricity CERN consumes. So I think, if I remember correctly, I have stood inside the CERN control center where they control all of the accelerators, and they have this very nice little thing on the wall with these wheels that show, the total electricity use. And I think while the LHC and all of its experiments are running,
Hey.
I think that it takes something like 175 megawatts.
Yes, exactly.
When they're all running. When in 2011, so the LHC started in 2008, and then there was a bit of an accident, so we had to do some fixing. So it started on again end of 2009. 2010, we took a bit of data. 2011, we took some more data, and we were starting to see hints of what we thought might be this new boson. And
sorry,
cool.
To some.
And so the CERN directorate decided that they would run. Normally, we would shut down at like in November, but they were going to run until the middle of December with the LHC. And I think that just that extra running added an extra like million Swiss francs onto the electricity cost.
Just for electricity, right? No.
Yeah, just in additional electricity costs.
Power and other stuff.
Yeah. So
but this year we will be running until December.
This year we're going to be running until the 6th of December. So it's going to be another intense year.
Looking
And
forward to it.
Yeah. And then we've got another short run next year.
Until summer, probably.
Till
if
June.
everything goes well for the upgrades,
Yeah.
then we'll see.
And then we're gonna
another
shut
fun
down.
will start.
Yeah, and then we're going to shut down for a number of
Doing a
years.
lot of
We're going to take out the entire center of CMS, the tracking detector, and we're going to be replacing it with a completely new tracking detector. Also, some of the
calorimeters will be completely changed as
Yeah.
well with the new technology.
Yeah, so this will take us till about 2029, 2030.
It will be the operation.
And then we'll start up again with a brand new. And now in what we're calling this next phase from 2030 onwards, we call it the high luminosity LHC. So at the moment, we have these bunches of protons, and there's about 100 billion protons in each bunch.
So there is a question from outsider.
Oh.
what is luminosity? It's a good question. Physicists don't understand, but it's the intensity. It's like the how to say the rate of the collisions. We can say it's like,
how many
collisions
we
happening,
get.
such that the probability of getting a known process is higher, basically.
Right.
The higher the luminosity is, the higher you shine on the two protons, basically, and you get the probability
That's why
of
it's called luminosity.
yes, exactly. It's just luminous. It's a light
Physicists,
thing, but it has nothing to do with light.
us
It's just a-
physicists love to take words
an
from
area.
other things
Yeah.
and then use it.
It's
Like,
an inverse area in
yeah.
terms of.
Like if you ever want to make a physicist, go, ask them to explain the spin of a particle.
It turns, but it doesn't turn.
It's like we say an electron,
There's an analogy.
an electron has spin. We say it's got spin, but it's
not turning.
It's not spinning.
Because
It's
it's a
not
point-like
actually
particle,
spinning. Yeah, it's a
yeah.
pointer. It can't even spin. But it's
a quantum, like the colors.
yeah, it's got
Explain
something.
the colors of QCD.
It's got something.
not red.
If you write down the description of
mathematical
that
description.
in mathematics, then mathematics looks like angular momentum. So we call it.
We use the analogy for colors
Yeah.
for QCD because we have
Exactly.
three colors.
Exactly.
They match,
Exactly.
makes white. All the final steps are white, but the quarks themselves they don't.
They don't have
they don't
color.
have
So
They don't see
luminosity.
them color.
Luminosity is another one of these words.
Quantum identity. It's a number of.
And in addition, the
unified
beauty
theory.
quark is not beauty at all.
No, it's
we
a
call it
case.
bottom. We call it bottom.
We call it. Yeah,
I
it's
use the
definitely
bottom more.
Yeah,
Oh,
same.
yeah.
And top and bottom, it just
Top and bottom,
works
it makes
better.
more sense.
Yeah.
Yes.
But anyway,
Strange and charm. It's also
The
quite
charm,
strange.
yeah.
It's not
Charm.
charmy,
yeah.
but it's quite charmy. Japes are quite charming.
All right.
Sorry.
Thank you very much. We're going to have to start wrapping up here.
Sorry. You're dragged here.
We have I have one more question before we have to let the students go. But like, what do you like about working at the LHC, or what's it like being there at CMS?
I mean, this very same moment, like we exchange ideas even while during a visit. I learned at least 5 stuff. Now I will go back and watch the video to remember them all. And all the exchanges in this international environment that we do here, with the sole motivation of doing science, is so precious, and it keeps us doing what we are doing despite all the difficulties and everything. And I still love my job, and I would like to continue for that, at least until I can.
Yeah, absolutely. Like every day you are learning something new. You're probably doing something you've never done before. Every day is different. One week I was building a bit of detector and building that and putting it together. The next week I'm, just catching up on emails and doing documentation and stuff. And then the next week, now it's time to start up the experiment. So, we're working here and getting that done. It's a really, it's a new experience every single day. And the people are fantastic as well, because we're in a collaboration with 5,000 people, but everybody loves this stuff. So, you'll sit here with some random people and you'll start getting into a conversation of words.
And hours. Like we have shift blocks of 8 hours, and I never remember any single shift that I was bored.
Yeah.
Even though we were taking data continuously, and there was no button to touch for no one. We had things to discuss, and it was always fun to be here. So.
And the people as well are like fascinating. We have what is your hobby? Like, what do you do?
I play table tennis, and then you start, and then you invite someone to go to table tennis club, and
and there are
voila.
people who've got bands, rock bands.
Music
there are, there's people who are rock climbers. I think there's somebody in the IT department who was a Paralympian skier.
We were playing chess once. I had my small chess board with me, and we were playing in the old classroom, obviously. But
there is a solar club.
There's a solar club. There's all sorts of things. Sailing, running, whatever. Rugby club. Yeah, there's the rugby team.
Table tennis club exists, by the way. And part of it. It's an advertisement.
So yeah, definitely. If you come to CERN, you'll never be bored.
Excellent. Thank you all very much on the CMS side. Let's thank our CMS team.
Thank you so much. And thank you to Zoltan and Noemi, who are hiding behind the cameras and helping make this work. Thank you for the excellent talk.
Thanks to you.
Yeah,
Bye,
thank you so much. I
everyone.
know here it's Saturday morning physics, but I know it's a Saturday evening for you all. So thanks so much for taking the time out of your day. We really appreciate it.
Never a bad time to do good physics.
Exactly.
I will note there are a lot of U.S. universities that work on CMS on this experiment. So if you're like interested in research, you know, as you're starting to apply to colleges, there's a lot of places that you could apply. You know,